What if everything you see, touch, and experience is nothing more than an elaborate illusion? What if the universe you know is just one layer of something far stranger, far more mysterious? Strap in, because we're about to take a wild ride through 50 mind-bending theories about the true nature of reality. Ideas so strange, they'll make you question everything. From simulated worlds to holographic universes, from consciousness shaping existence to the possibility that time itself is an illusion, we're diving deep into the most fascinating, controversial, and downright bizarre explanations for why things are the way they are. Some of these theories come from cutting-edge science, others from ancient philosophy, and a few might sound like science fiction until you hear the evidence. So get ready to have your perspective shattered, because by the end of this journey, you might never look at reality the same way again, and who knows? One of these theories might just feel true. Let's begin. Now let's step into the first theory, one that might feel ripped straight from a sci-fi movie, but is taken seriously by some of the brightest minds today. Picture this: what if our entire universe, from the stars above to the phone in your hand, is nothing more than an ultra-advanced simulation? This is the core of simulation theory, and it's not just wild speculation. Philosopher Nick Bostrom laid out a compelling case with his ancestor simulation argument. He suggests that a future civilization with immense computing power might choose to recreate their past, meaning us as a kind of historical reenactment. The logic is eerily simple. If such simulations are possible, the number of simulated realities could vastly outnumber the one base reality, making it statistically likely we're in one. Modern technology adds fuel to this fire. Virtual reality keeps advancing at breakneck speed, blurring the lines between the digital and the physical. If we're already crafting immersive worlds, why couldn't a more advanced species do the same but flawlessly? Even Elon Musk has thrown his weight behind the idea, famously stating the odds we're in base reality are 1 in billions. But what would this mean for us? If true, it ripples through philosophy, science, even ethics. Are our choices truly ours, or lines of code in a cosmic program? Could glitches in reality, like déjà vu or quantum oddities, be hints of the simulation's framework? Skeptics argue we'd need irrefutable proof, like finding a literal error message in the fabric of physics. Yet the question lingers: if reality is a simulation, does that make it any less real to us? After all, here we are questioning it, just as the simulators might have intended. Now, let's dig deeper into the evidence and the pushback surrounding simulation theory. If our reality is a simulation, where might we spot the seams? Some point to quantum mechanics, where particles behave unpredictably until observed. Could this indeterminacy be a sign of computational shortcuts, like a simulation conserving processing power by only rendering details when needed? Others highlight oddities like déjà vu or mathematical constants that seem suspiciously fine-tuned, as if programmed for stability. Even the speed of light, an unbreakable cosmic limit, could be seen as a built-in buffer to prevent the simulation from overloading. But physicists aren't so quick to accept these as proof. They argue that quantum weirdness has natural explanations, like wave function collapse, and that fine-tuning might just reflect our universe's unique physics among countless others in a multiverse. Then there's the practical challenge. How would we even test simulation theory? Some propose hunting for pixelation in spacetime at the smallest scales or anomalies in high-energy particle collisions. Yet critics counter that any glitches we find could just be gaps in our current understanding, not proof of a simulated world. The debate boils down to this: without a way to distinguish between a flawless simulation and base reality, does the question even matter? After all, whether coded or cosmic, reality feels just as real to us. But if we ever did uncover irrefutable evidence, it would reshape everything from science to spirituality. So here's the ultimate thought experiment. If you could press a button to reveal the truth, would you dare to? Now, let's turn our attention to a theory that flips our understanding of reality on its head, literally. Imagine the entire universe as a grand cosmic illusion, where the three-dimensional world we experience is nothing more than a projection from a two-dimensional surface. This is the holographic principle, a mind-bending idea that suggests our reality might be akin to a hologram, with all the information encoding our existence stored on a distant, flat boundary. At the heart of this theory lies the work of physicist Leonard Susskind, who, along with others, proposed that the universe could function like a hologram. How does this work? Think of it like a movie screen. Everything you see in three dimensions, the depth, the movement, the textures, is actually encoded on a flat, two-dimensional surface. Similarly, the holographic principle argues that all the information about every particle, every force, and every event in our universe could be inscribed on a boundary far away from our everyday experience. This idea finds strong support in string theory and black hole thermodynamics. When scientists study black holes, they encounter a puzzling fact. The amount of information a black hole can hold seems to depend not on its volume, but on the area of its event horizon. This revelation led to the groundbreaking notion that information, and by extension, reality itself, might be fundamentally two-dimensional, with our three-dimensional world emerging from it like a holographic projection. One of the key frameworks supporting this idea is the anti-de Sitter/conformal field theory correspondence, or AD-S/CFT. Without diving too deep into the math, this principle suggests a profound equivalence between a gravitational theory in a higher dimensional space and a quantum field theory on its lower dimensional boundary. In simpler terms, it's like saying the rules governing a three-dimensional world could be entirely described by physics operating on a two-dimensional surface. So, what does this mean for us? If the holographic principle holds true, it challenges our most basic assumptions about space, time, and reality itself. It implies that the solid, tangible world around us might be nothing more than an incredibly detailed projection, with the true source code of existence lying on some distant, flat cosmic canvas. Next, we'll explore how this theory reshapes our understanding of physics and what it could reveal about the very fabric of the universe. Now, let's unpack what the holographic principle means for physics as we know it. This idea doesn't just suggest a quirky twist on reality, it outright challenges some of the most fundamental assumptions about space and time. Classical physics treats space-time as a smooth, continuous stage where events unfold. But if the universe is a hologram, that stage might be an illusion, with the real action happening on a distant, two-dimensional surface. Take black holes, for example. Normally, we'd expect the entropy, a measure of disorder inside a black hole, to depend on its volume. But startlingly, it scales with the area of its event horizon instead. This hints that the information describing everything inside the black hole could be encoded on its surface like a cosmic hard drive. It's a radical departure from classical thinking, suggesting that the 3D world we perceive might just be a projection of deeper 2D physics. Scientists are actively searching for evidence of this holographic nature. One approach involves hunting for holographic noise, tiny fluctuations in spacetime that could betray its underlying pixelated structure. Experiments like the holometer at Fermilab aim to detect these minuscule ripples by measuring interference patterns with ultra-precise lasers. While no smoking gun has been found yet, the very possibility has physicists rethinking the fabric of reality. This theory also forces us to reconsider gravity. In a holographic universe, gravity might not be a fundamental force but an emergent phenomenon, arising from the way information is entangled on that distant boundary. It's like realizing the plot of a movie isn't driven by the actors on screen, but by the code running the projector behind the scenes. The implications stretch beyond black holes and lab experiments. If space-time is holographic, it could reshape our understanding of the Big Bang, quantum mechanics, and even the nature of consciousness. Next up, we'll dive into an even stranger idea, Boltzmann Brains, and ask whether self-awareness could emerge from pure randomness in the void of space. Now let's shift gears to something even more mind-bending. The concept of Boltzmann Brains. Imagine for a moment that a fully conscious, self-aware entity could just pop into existence out of nowhere, floating in the emptiness of space. No body, no history, just a lone brain with memories and thoughts conjured from pure randomness. That's the essence of this bizarre theory, named after physicist Ludwig Boltzmann, who explored the strange implications of thermodynamics and entropy. At its core, this idea stems from the second law of thermodynamics, which tells us that entropy, or disorder, always increases over time. But in an infinite universe, given enough time, even the most unlikely events can happen. So, statistically, it's possible for particles to randomly arrange themselves into a functioning brain, complete with false memories of a past that never existed. It's like shaking a box of puzzle pieces for eternity until, by sheer chance, they form a perfect picture. But here's the twist: most scientists dismiss this idea, even though the math technically allows it. Why? Because if Boltzmann brains were real, they'd be far more common than ordinary, biologically evolved minds like ours. After all, it's astronomically easier for particles to randomly assemble a single brain than an entire universe teeming with life. So, if Boltzmann brains dominate reality, why does our universe seem so stable and ordered? This paradox forces physicists to question whether the theory is a fascinating thought experiment or a dead end. Critics argue that the sheer absurdity of Boltzmann brains undermines their plausibility. If we accept them, we'd have to doubt whether our own memories and experiences are real or just fleeting flukes in the void. It's a philosophical quix, and that leaves even the boldest thinkers uneasy. Yet, the theory persists because it challenges our assumptions about time, consciousness, and the nature of existence itself. Next, we'll explore how this idea connects to cosmic inflation and alternate theories of reality, diving deeper into the rabbit hole of what might truly lie beneath the surface of our universe. Now, let's take this idea even further and see how Boltzmann brains weave into the grand tapestry of cosmic inflation. Picture our universe not as a one-time event but as part of an endless multiverse, bubbling with new universes constantly sprouting from the fabric of space-time. In this infinite sea of possibilities, the conditions for Boltzmann brains become not just probable but inevitable. If inflation never stops, if new universes keep budding off with different laws of physics, then somewhere out there, a random fluctuation could indeed spit out a fully formed consciousness. But here's where things get even stranger. The multiverse doesn't just offer a home for Boltzmann brains, it also presents an alternative escape from their unsettling implications. Some theorists argue that if inflation naturally produces orderly, life-friendly universes like ours, then these stable regions would vastly outnumber the chaotic voids where Boltzmann brains might emerge. Suddenly, the odds tip in favor of us being real, evolved beings rather than fleeting cosmic accidents. This brings us to a sharp contrast with another pillar of physics, the Copenhagen interpretation of quantum mechanics. While Boltzmann brains thrive in the realm of infinite randomness, the Copenhagen interpretation grounds reality in observation. It says particles don't settle into definite states until they're measured, implying that consciousness plays a central role in shaping the universe. No mysterious floating brains required, yet both theories push us to the edge of scientific comfort. On one side, Boltzmann brains force us to question whether anything we know is real. On the other, the Copenhagen interpretation leans on the slippery idea that reality might not exist without observers. One feels like a cosmic prank, the other a philosophical tightrope walk. So which is more plausible? The answer depends on whether you trust the math of infinite chaos or the pragmatism of observed reality. Either way, the debate reveals just how deeply weird our universe could be and how much we still have to unravel. Next, we'll dive into another radical idea that flips our understanding of reality on its head: eternal inflation, where the cosmos isn't just expanding but birthing new universes endlessly. Now, let's shift our gaze to a theory that stretches the very fabric of reality beyond comprehension: eternal inflation. Imagine our universe isn't just expanding but giving birth to countless others, each with its own unique set of physical laws. This idea, pioneered by physicist Alan Guth, suggests that the rapid expansion we call cosmic inflation never truly stops. Instead, it creates a never-ending cascade of new universes, like bubbles constantly forming in an infinite cosmic foam. At the heart of this theory lies a startling implication. If inflation is eternal, then somewhere out there, an infinite number of universes exist, each with slight or dramatic variations in their fundamental constants. Some might have stronger gravity, others might lack dark matter entirely, and a few could even harbor bizarre forms of life we can't begin to imagine. But here's where it gets personal. In this endless multiverse, there could be worlds where versions of you made different choices, took different paths, or even live under entirely different laws of physics. The math behind eternal inflation is both elegant and mind-bending. Guth's work shows how quantum fluctuations during the universe's earliest moments could trigger regions of space to stop inflating, forming isolated pocket universes like ours, while the rest of space continues expanding eternally. This isn't just speculation, it's a direct extension of the inflation theory that explains so much about our own universe's smoothness and structure. But eternal inflation raises a dizzying question. If there are infinite universes, does that mean every possible version of reality exists? Could there be a world where dinosaurs never went extinct, or where you're the ruler of a galactic empire? The answer, mathematically at least, leans toward yes. Yet this also leads to what physicists call the measure problem. How do we calculate probabilities in a landscape where everything that can happen does happen infinitely? Eternal inflation doesn't just challenge our place in the cosmos, it redefines what the cosmos even means. And as we peel back these layers, one thing becomes clear: reality might be far stranger and far more abundant than we ever dared to dream. Next, we'll explore how this bubbling multiverse might leave clues in our own universe and whether we can ever find them. So, if eternal inflation paints a picture of an endless multiverse, how could we ever find proof? Let's turn our attention to the cosmic microwave background, the ancient afterglow of the Big Bang. This faint radiation blanket holds subtle temperature variations, and some physicists argue these imperfections might be cosmic breadcrumbs left behind by collisions between our universe and neighboring bubble universes. Imagine finding a fingerprint pressed into the fabric of space itself, evidence that another universe once brushed against ours. The idea hinges on spotting unusual patterns in the microwave background, like unexpected cold spots or asymmetries that standard cosmology can't explain. While no definitive collision signature has been confirmed, anomalies like the so-called axis of evil, a puzzling alignment of temperature fluctuations, keep the door open for wild possibilities. Could these be echoes of a long-ago encounter with another universe? It's a tantalizing thought, but skeptics point out alternative explanations like instrumental errors or local astrophysical effects. Then there's the measure problem, a thorn in the side of multiverse theories. If infinite universes exist, how do we calculate the odds of anything? For example, if 99.9% of universes are lifeless voids, but infinite versions harbor life, does that mean life is almost impossible or guaranteed? This isn't just philosophical quibbling. Without a way to weight probabilities, even the most elegant multiverse theory struggles to make testable predictions. Critics argue this pushes eternal inflation into the realm of metaphysics rather than physics. Yet, researchers haven't given up. Some propose that advanced gravitational wave detectors or deeper scans of the cosmic microwave background might uncover hints of bubble universe collisions. Others suggest looking for exotic particle signatures that could have leaked into our universe from a neighboring one. While the challenges are immense, the stakes couldn't be higher. Confirming eternal inflation wouldn't just rewrite textbooks, it would redefine our understanding of reality itself. Now, let's pivot to a theory that takes quantum mechanics into even stranger territory, a world where every decision spawns entirely new universes. Welcome to the many worlds interpretation. Here's where reality takes a sharp turn into the truly bizarre. Picture this: every time you make a decision, whether it's choosing coffee over tea or turning left instead of right, the universe doesn't just follow one path. According to the many worlds interpretation, it splits. Every possible outcome happens, each in its own newly born universe. This idea, dreamed up by physicist Hugh Everett in the 1950s, suggests our reality is just one thread in an endlessly branching tapestry of parallel worlds. To wrap your head around this, think back to Schrödinger's infamous cat, the one trapped in a box with a 50-50 chance of survival. In the classic view, the cat is both alive and dead until someone checks. But Many Worlds flips the script. There's no spooky in-between state. Instead, the moment the quantum trigger decides the cat's fate, reality divides. In one universe, the cat purrs happily. In another, it doesn't. Both outcomes are equally real, just happening in separate, unconnected branches of existence. Now, here's where things get sticky. If every quantum event spawns new universes, why do we perceive a single, stable reality? This is the preferred basis problem. The math of quantum mechanics doesn't explain why we experience one specific outcome, say, a living cat instead of a jumbled mix of possibilities. Everett argued that consciousness itself might split along with the universe, meaning every version of you thinks their outcome is the only one. But critics ask, if there's no way to test or interact with these other worlds, does the theory even count as science? Supporters counter that Many Worlds solves some of quantum mechanics' biggest headaches, like the mystery of wave function collapse. No need for observers or magical disappearances of possibilities, just an ever-expanding multiverse where every quantum roll of the dice lands in some universe. And while we can't hop between branches yet, physicists have proposed wild experiments like measuring tiny quantum systems to see if their behavior hints at echoes from parallel realities. So is our universe one of countless copies, each playing out every conceivable variation of existence? The Many Worlds interpretation doesn't just challenge our place in reality, it obliterates the idea of a single objective now. Next up, we'll push this idea to its unsettling limit with a thought experiment that asks, what if you could never die? Now, let's dive into one of the most unsettling thought experiments tied to the Many Worlds interpretation: quantum suicide. Imagine a scenario where a person is hooked up to a device that measures a quantum event like the spin of an electron. If the electron spins one way, the device does nothing. But if it spins the opposite way, the device triggers a lethal outcome. According to Many Worlds, every time the device is activated, the universe splits. In one branch, the person dies. In another, they survive. From the survivor's perspective, the device keeps failing to fire, no matter how many times it's tested. To them, it's as if they're invincible because in every universe where they continue to exist, the deadly outcome never happens. This idea raises chilling questions. If consciousness really does split across parallel worlds, does that mean you could never experience death? Some argue this thought experiment suggests a kind of immortality. Your awareness would always follow the path where you survive, no matter how unlikely the odds. But here's the catch: this only works from your subjective viewpoint. Everyone outside the experiment would still observe you as either alive or dead, depending on the outcome in their own branch. Ethically, this experiment is a nightmare. even as a hypothetical, it forces us to grapple with whether consciousness is truly bound by probability or if it somehow chooses the favorable outcome. Critics point out the glaring flaw. If many worlds is correct, there are still branches where you don't survive, meaning the experiment doesn't actually prove anything about immortality. It just highlights how our perception of reality might be limited to a single thread in an infinite tapestry. Beyond the ethical dilemmas, quantum suicide also ties back to the observer effect in quantum mechanics. If an outcome only becomes real when observed, does consciousness play a special role in shaping reality? Or is this just an illusion created by the branching of worlds? Supporters of many worlds argue that consciousness isn't magical, it's just another physical process caught up in the splitting universes. But opponents say this thought experiment exposes the absurdity of taking the theory too literally. Ultimately, quantum suicide doesn't offer easy answers. Instead, it forces us to confront the strangest implications of parallel realities, where death might be inevitable in some worlds and impossible to experience in others. Next, we'll explore a theory that flips the script entirely, proposing that consciousness isn't just a passenger in reality, but the very foundation of it. Moving beyond the eerie implications of quantum immortality, let's turn to a theory that reshapes how we think about consciousness itself: panpsychism. This idea suggests that consciousness isn't something that magically emerges in complex brains, but is instead a fundamental feature of the universe, present even in the tiniest particles. Imagine every atom, every speck of matter carrying some tiny spark of awareness. It's a perspective that stretches back to ancient philosophers like Thales and Plato, who pondered whether the cosmos itself might be alive in some way. Fast forward to today, and thinkers like Galen Strawson argue that panpsychism solves one of the biggest puzzles in science: how subjective experience arises from purely physical processes. If consciousness is already woven into the fabric of reality, then there's no need to explain how it suddenly appears in humans or animals. It's been there all along, just organized in different ways. This stands in stark contrast to emergent materialism, the mainstream view that consciousness pops into existence once brains reach a certain level of complexity. But how does this actually work? Panpsychists don't claim electrons are pondering philosophy. Instead, they propose that even the simplest particles have a bare minimum of experience, what philosopher David Chalmers calls proto-consciousness. When these particles combine in intricate systems like our brains, those tiny sparks of awareness merge into the rich inner lives we know. It's like pixels forming a picture. Individually, they're just dots of color, but together they create something vastly more complex. Critics, of course, have their doubts. If everything is conscious, they ask, why don't rocks or smartphones exhibit thoughts? Panpsychists respond that consciousness isn't all or nothing, it scales with complexity. A rock's experience, if it exists at all, would be unimaginably simple compared to ours. Others argue that panpsychism merely relabels the mystery of consciousness without explaining it. Yet for many, this view offers an elegant middle ground between dismissing consciousness as an illusion and invoking supernatural explanations. What makes panpsychism so compelling is its potential to bridge science and spirituality. It hints at a universe where matter and mind aren't separate but deeply intertwined. Next, we'll explore how modern science is testing these radical ideas and whether they could rewrite our understanding of reality itself. Shifting gears to the cutting edge of consciousness research, let's see how panpsychism holds up under the lens of modern science. One of the most intriguing frameworks supporting this idea is integrated information theory, or EIT, developed by neuroscientist Giulio Tononi. Unlike traditional approaches that focus solely on brain activity, IIT proposes that consciousness arises from the way information is organized and interconnected within a system. The more integrated and complex the information flow, the richer the conscious experience. This theory doesn't just apply to brains, it suggests that any system with the right kind of connections, whether biological or artificial, could have some level of awareness. But how does this tie into panpsychism? IT implies that even simple systems, like a network of neurons or a basic computer circuit, might possess a faint glimmer of consciousness if they meet certain mathematical criteria. This lends scientific weight to the idea that experience isn't exclusive to highly evolved organisms, but could be a universal feature of organized matter. Some researchers have even used IT to explore whether devices like cameras or thermostats could have rudimentary forms of sensation, though the implications remain hotly debated. Of course, the question that naturally follows is, could rocks be conscious? Under IT, a random chunk of granite likely wouldn't qualify. Its atoms lack the organized complexity needed for integrated information. But panpsychists argue that even if rocks don't think, their fundamental components might carry traces of proto-consciousness. This leads to wild thought experiments. If you ground a rock into dust, would its microscopic particles retain some sliver of experience? It's a staggering idea, and one that pushes the boundaries of both physics and philosophy. Neuroscience, meanwhile, offers its own challenges. Critics point out that brain scans show clear correlations between neural activity and conscious states, suggesting that consciousness emerges from biological processes rather than being intrinsic to matter. Yet panpsychists counter that these findings don't rule out their view. They might simply reveal how simpler forms of awareness combine into the vivid experiences we recognize. The debate is far from settled, but what's fascinating is how panpsychism forces us to rethink the very definitions of life, intelligence, and reality. As we piece together these puzzles, one thing becomes clear: the line between mind and matter might be far blurrier than we ever imagined. Up next, we'll dive into another radical perspective: idealism, which flips the script entirely by proposing that reality is purely mental. Could the physical world be nothing more than a projection of consciousness? Let's explore. Now, let's take a step into a perspective that turns everything we think we know on its head: the philosophy of idealism. Unlike materialism, which insists that the physical world is the foundation of reality, idealism flips the script entirely. It proposes that reality is fundamentally mental, nothing more than a projection of consciousness. This isn't some new age concept. It has deep roots in history, championed by thinkers like George Berkeley, who argued that to be is to be perceived. Without a mind to observe it, Berkeley claimed, the material world simply doesn't exist. Eastern philosophies have echoed this for centuries. Traditions like Advaita Vedanta teach that the physical universe is an illusion, or Maya, and that pure consciousness is the only true reality. But how does this hold up in the modern world? Surprisingly, some interpretations of quantum mechanics seem to dance uncomfortably close to idealism. The famous observer effect suggests that particles don't have definite states until they're measured, implying that consciousness might play a role in shaping reality itself. Critics, of course, push back hard. Materialists argue that the observer effect doesn't require a human mind. Any interaction with the environment could collapse a quantum state. But idealists counter that this just moves the goalposts. What if the entire universe is a vast, interconnected mind? Some even speculate that the mathematical elegance of physics hints at a reality more like a grand thought than a collection of objects. The debate forces us to confront a staggering question. If idealism is true, what does that mean for our everyday experience? Are the people, places, and things around us just fragments of a shared dream? Or is there a deeper layer of consciousness weaving it all together? Whether you find it inspiring or unsettling, idealism challenges us to rethink the very fabric of existence, and that's a journey worth taking. Up next, we'll dig deeper into how consciousness might shape reality by exploring quantum mind theories. Could our thoughts literally bend the laws of physics? Let's find out. Now, let's dive into one of the most mind-bending intersections of science and philosophy, the idea that consciousness doesn't just observe reality but actively shapes it. Enter quantum mind theories, which propose that our thoughts might have a direct hand in collapsing the probabilities of quantum mechanics into the solid world we experience. At the heart of this idea is the work of physicist Sir Roger Penrose and anesthesiologist Stuart Hameroff, who teamed up to propose something called orchestrated objective reduction, or ORCH for short. They suggest that consciousness arises from quantum processes happening inside the microscopic structures of our brain cells, specifically tiny tubes called microtubules. According to their theory, these microtubules act like quantum computers, processing information in ways classical physics can't explain. When a quantum state inside them collapses, it generates a moment of conscious awareness. But why would nature rely on such an exotic mechanism? Penrose argues that human cognition involves processes like understanding or creativity that can't be replicated by conventional algorithms. There's a kind of non-computable magic to our thinking, something that might only make sense if quantum physics is involved. Hameroff, meanwhile, points to how anesthesia works. It selectively switches off consciousness by disrupting these quantum vibrations in microtubules, leaving other brain functions intact. If they're right, the brain isn't just a biological machine, it's a quantum orchestra. Of course, not everyone's convinced. Critics highlight that the warm, wet environment of the brain seems too chaotic for delicate quantum states to survive long enough to matter. Decoherence, the tendency for quantum systems to dissolve into randomness when exposed to their surroundings, should wipe out any quantum effects almost instantly. And while Penrose and Hameroff have refined their model over the years, mainstream neuroscience remains skeptical, favoring classical explanations for consciousness. Yet, the allure of quantum mind theories persists. If consciousness really does play a role in collapsing wave functions, it would mean our minds are far more than passive observers, they're active participants in shaping reality itself. Whether ORCH holds up or not, it forces us to grapple with a profound question. Could the universe be built not just on matter and energy, but on the very fabric of thought? Next, we'll venture into another radical framework for reality, loop quantum gravity, where even space-time itself gets a quantum makeover. What if the continuity of the universe is just an illusion? Stay tuned. Taking a step into the unknown, let's explore a theory that reimagines the very fabric of space-time. Loop quantum gravity challenges the smooth, continuous universe we think we know, proposing instead that reality is stitched together from tiny, indivisible threads. Picture space-time not as an endless sheet but as a vast, dynamic web of interconnected loops. A spin network where each knot and link represents the smallest possible units of space and time. Leading this revolutionary idea is physicist Carlo Rovelli, whose work suggests that gravity emerges from these quantum loops interacting with one another. Unlike string theory, which imagines tiny vibrating strings in higher dimensions, loop quantum gravity keeps things grounded in the familiar 4 dimensions, but with a twist. Here, space itself is granular, like a digital image made of pixels, but so fine we'll never perceive the graininess directly. One of the most dramatic implications of this theory. The Big Bang might not have been the beginning after all. Instead of a singularity, a point of infinite density where physics breaks down loop quantum gravity proposes a quantum bounce. Imagine the universe collapsing under its own gravity, reaching a tiny but finite size, then rebounding outward like a spring. This could mean our cosmos is just one chapter in an endless cycle of expansion and contraction. But how does this hold up against string theory? While both aim to unify quantum mechanics and gravity, they take wildly different paths. String theory adds extra dimensions and relies on mathematical elegance, whereas loop quantum gravity sticks to observable dimensions and focuses on the quantum structure of space itself. Critics argue that loop quantum gravity struggles to explain how smooth spacetime emerges from its granular building blocks, while supporters counter that it offers a more direct path to reconciling Einstein's general relativity with quantum weirdness. Whether loop quantum gravity ultimately proves correct or not, it forces us to rethink the nature of reality at its most fundamental level. If spacetime is truly granular, then even the vacuum of empty space might be teeming with quantum activity, a buzzing network of relationships waiting to be decoded. Next, we'll peel back another layer of this mystery. What if time, as we experience it, is nothing more than an illusion? Now, let's unravel another mind-bending layer of loop quantum gravity. What if time isn't real? This theory doesn't just reshape space, it dissolves time as we know it. Imagine a universe where the past, present, and future aren't flowing but exist all at once, frozen in a vast, unchanging block. Loop quantum gravity hints at this possibility by suggesting that time might emerge from deeper, timeless physics, like a movie appearing to move when you play its static frames in sequence. Enter physicist Julian Barber, who takes this idea even further with his concept of time capsules. Picture reality as a collection of frozen moments, each containing the illusion of a past and future. According to Barber, what we call time is just our brain's way of stitching these snapshots together into a coherent story. Think of flipping through a photo album. Your memory creates the sense of time passing, even though each photo exists independently. So why does time feel so real? Our perception plays tricks on us. Just as a spinning wheel appears solid, the constant chatter of quantum interactions in our brains generates the illusion of flow. Experiments in neuroscience back this up. Our brains construct time by integrating sensory inputs, like a conductor orchestrating a symphony from scattered notes. Even Einstein hinted at this, calling the distinction between past and present a stubbornly persistent illusion. But if time is an illusion, how does loop quantum gravity explain causality, the idea that causes precede effects? Here's where things get fascinating. In a timeless universe, causality isn't about sequence but correlation. Events aren't linked by time but by quantum relationships, like dots connected in a cosmic dot-to-dot puzzle. Supporters argue this aligns with quantum mechanics, where particles instantly influence each other across space. No time required. Critics, of course, raise eyebrows. If time isn't fundamental, why does entropy always increase, or why do we remember the past but not the future? Loop quantum gravity responds by pointing to emergent properties. Just as temperature arises from atoms jiggling, the arrow of time might emerge from the universe's underlying quantum structure. Whether time is real or not, this theory forces us to question one of our most basic experiences. Every tick of the clock, every sunrise, could they just be fragments of a deeper, timeless reality? Up next, we'll encounter a theory where time doesn't just bend, it crystallizes. Now, let's step into a realm where time itself takes on a strange new form: time crystals. These bizarre structures, first proposed by Nobel laureate Frank Wilczek, aren't just a fleeting idea, they're real, and they challenge one of the most fundamental laws of physics: entropy. Picture a snowflake, but instead of repeating in space, its pattern repeats in time. That's the essence of a time crystal, a system that cycles through states indefinitely, without any energy input, like a clock that ticks forever without winding. Unlike everything else in our universe, which tends toward disorder over time, time crystals resist this decay, maintaining their rhythmic motion even in their lowest energy state. It's as if they've found a loophole in thermodynamics. How is this possible? Normally, perpetual motion is forbidden. Energy gets lost to friction, heat, or other forces. But time crystals exploit quantum mechanics to sidestep these limits. In 2016, researchers created the first time crystals in the lab using chains of ions or defects in diamonds. These systems don't violate the laws of physics. Instead, they reveal a hidden layer where time symmetry breaks spontaneously. much like how water freezing into ice breaks spatial symmetry. So, could time crystals rewrite thermodynamics? Not entirely, but they do force us to rethink its boundaries. Traditional thermodynamics assumes systems eventually settle into equilibrium, yet time crystals never do. They keep oscillating, hinting at entirely new phases of matter where time itself becomes an ordered dimension. Some physicists speculate they could lead to ultra-precise quantum clocks or even unhackable quantum memory. Of course, skeptics ask, if these structures are locked in repetitive motion, do they actually do anything useful? The answer might lie in quantum computing, where stable, coherent states are gold, and time crystals could provide just that. As we untangle this paradox, one thing is clear: time crystals prove reality still holds surprises. Next up, we'll explore how these strange temporal structures might exist not just in labs, but across the cosmos. Now, let's take this idea even further, because time crystals aren't just lab curiosities. They could revolutionize how we store and process information. Imagine a form of quantum memory so stable it never degrades, thanks to the unbreakable rhythm of time crystals. In quantum computing, where fragile qubits lose coherence in the blink of an eye, these structures could act like anchors, preserving data in their perpetual oscillations. Researchers are already exploring how time crystals might lock in quantum states, creating error-resistant systems that don't just push the boundaries of physics, they could redefine the future of technology. But what if time crystals aren't confined to Earth? Picture this: deep in the fabric of space, where temperatures near absolute zero and quantum effects dominate, could cosmic-scale time crystals exist? Some theories suggest neutron stars, with their extreme magnetic fields and bizarre matter, might host natural versions of these structures. Others speculate that the early universe itself, in its hyper-energetic infancy, might have birthed fleeting time crystals, echoes of an order we're only beginning to understand. Whether in quantum labs or the cold expanse of space, one thing's certain: time crystals hint at a hidden layer of reality where time isn't just a backdrop but an active player. And if we can harness their strange properties, we might unlock doors to technologies and cosmic mysteries we've barely dreamed of. Up next, we'll dive into a theory that turns the universe inside out, literally. The idea that our entire cosmos might exist within a black hole. Now, let's pivot to a theory that flips our cosmic perspective inside out, literally. Imagine our entire universe not as an expanding void but as something far stranger: the interior of a black hole. This is the mind-bending premise of black hole cosmology, a theory that suggests the Big Bang might have been the birth cry of a white hole, a black hole's hypothetical twin spewing matter outward instead of trapping it. The math behind this idea traces back to the Schwarzschild metric, a solution to Einstein's equations describing black holes. If you peer deep into those equations, they hint at a mirror universe on the other side of a black hole's singularity, a place where time runs backward and space unfurls anew. Some physicists, like Lee Smolin, take this further with the idea of fecund universes, where black holes act as cosmic wombs, birthing new universes with slightly tweaked physical laws each time. Think of it like a cosmic Russian doll. Every black hole in our universe could contain another universe, and inside that one, more black holes could spawn even more universes, a never-ending cascade of realities. It's a dizzying thought, but it offers a radical answer to why our universe seems so finely tuned for life. Maybe, just maybe, we're the product of an evolutionary chain of universes, each selected for its ability to create black holes and thus new cosmic offspring. Up next, we'll explore how this wild idea ties into one of black hole physics' biggest puzzles: the fate of information swallowed by these cosmic monsters. Does it vanish forever, or does it re-emerge somewhere or someone else? Now, let's untangle one of the most perplexing puzzles in black hole cosmology: the fate of information. When matter vanishes into a black hole, does it disappear forever, violating the laws of quantum mechanics, or is there a cosmic loophole? enter Stephen Hawking's groundbreaking idea: black holes aren't entirely black. They slowly leak energy known as Hawking radiation, evaporating over eons. But here's the catch: if the black hole vanishes, what happens to all the information it swallowed? This is where holography swoops in like a cosmic detective. The holographic principle suggests that everything inside a black hole might be encoded on its surface, like a three-dimensional movie stored on a two-dimensional screen. In other words, the information isn't lost, it's scrambled and preserved on the event horizon, waiting to be decoded. Some theorists argue this could mean black holes don't destroy information but transform it, potentially birthing new physics in the process. But the debate gets even wilder. If black holes do create new universes, as Smolens's fecund universe theory suggests, could that information resurface in a baby universe? Imagine secrets from our cosmos echoing in another reality, rewritten by the laws of that newborn universe. It's a tantalizing thought, yet critics point out the lack of evidence. How could we ever test such a claim? So, do black holes rewrite the rules of physics, or are they cosmic recycling centers for information? The answer might lie at the edge of our understanding, where quantum mechanics and gravity collide. One thing's certain: the deeper we dig, the stranger reality becomes. Now, let's shift gears and step into a world where reality might just be the ultimate computer program. Imagine the universe not as random cosmic soup, but as an intricate simulation running on unfathomable computational power. This is the core idea behind digital physics. Think of it like this: what if everything around us, from the tiniest particle to the largest galaxy, operates like lines of code in a vast quantum computer? One of the most fascinating takes on this comes from Stephen Wolfram, who suggests that simple rules called cellular automata could generate the complexity we see in nature. Picture a grid where each cell follows basic instructions, yet from that simplicity emerges everything from swirling galaxies to the patterns in a snowflake. If reality works this way, then even randomness might just be an illusion, a side effect of deeper, hidden algorithms at play. But Wolfram isn't alone in this thinking. Some physicists propose that the universe itself could be a quantum computer, processing information at the most fundamental level. Instead of particles and forces, reality might boil down to bits of data interacting in a cosmic computation. Quantum fluctuations may be just processing errors in the grand code. The Big Bang, a system boot up. Critics, of course, ask the obvious: who or what is running this program? Is there a cosmic programmer, or is computation just the natural language of reality itself? We don't have answers yet, but the idea forces us to rethink what existence truly means. If the universe is digital, then maybe science is reverse engineering the source code. So, is reality just an elaborate computation? Whether you find it thrilling or unsettling, digital physics undeniably reshapes how we see the fabric of existence, one algorithmic thread at a time. But as we peel back the layers of digital physics, we hit a fascinating roadblock: the limits of computation itself. Even in a universe that might operate like a quantum computer, there are boundaries imposed by the very fabric of reality. Take the Planck scale, for example, the smallest possible units of space and time. Below this scale, our current understanding of physics breaks down. It's like trying to run a program on a processor that can't handle anything smaller than a certain pixel size. The universe might have built-in resolution limits, making certain computations fundamentally impossible. This raises an even deeper question: is mathematics the language of reality, or is it just a human invention? Some, like Max Tegmark, argue that math isn't something we created, but rather something we discovered. His mathematical universe hypothesis takes this idea to the extreme, suggesting that reality isn't just described by math, it is math. In other words, the universe isn't merely running on mathematical rules, it's a mathematical structure itself. Every equation, every geometric shape might correspond to an actual physical existence somewhere in the multiverse. Of course, not everyone agrees. Critics point out that while math is incredibly effective at modeling reality, that doesn't necessarily mean reality is made of math. Could our reliance on mathematics simply reflect how our brains are wired to perceive patterns? Or is there something more profound at play, a universal code waiting to be fully decrypted? Whether math is invented or discovered, one thing's certain: the closer we look at the limits of computation, the more we realize how much we still don't understand about the true nature of reality. So, where does this leave us? If the universe operates like a computational system, then perhaps uncovering its ultimate rules isn't just about physics, it's about cracking the cosmic algorithm. And who knows, maybe the answer lies in a line of code we haven't even imagined yet. Now, let's shift our perspective entirely and step into the realm of non-dualism, a theory that challenges the very idea of separation. Unlike the computational models we've explored, non-dualism suggests that reality isn't divided into subjects and objects, observers and observed, but is instead a unified whole. This idea has deep roots in Eastern philosophies like Advaita Vedanta, which teaches that the perceived duality of the world, you versus everything else, is an illusion. At the core, there's only one undivided consciousness, and what we experience as individuality is just a temporary appearance, like waves on the surface of an ocean. But this isn't just an Eastern concept. Western thinkers like Spinoza argued something strikingly similar, that the universe and God are one and the same, a single substance with infinite attributes. Compare this to Cartesian duality, where René Descartes split reality into two separate realms, mind and matter. Non-dualism rejects that division outright. If digital physics frames reality as code, non-dualism frames it as a seamless, unbroken experience. So, is separation just an illusion? Think about it this way. When you look at a tree, science tells you that light reflects off it, enters your eyes, and your brain constructs an image. But in non-dualism, the tree, the light, and your awareness of it are all part of the same fabric. There's no real boundary, just an interplay within one existence. This raises profound questions. If everything is connected, does individuality even exist? Or are we all expressions of a deeper, singular reality? Skeptics, of course, point to the tangible world. How can a table and the person perceiving it be the same thing? Yet modern neuroscience offers intriguing parallels. Studies on meditation and psychedelics reveal moments of ego dissolution, where people report losing the sense of self entirely, merging into a boundless whole. It's as if the brain's usual filters, the ones that create the illusion of separation, temporarily shut off. Whether non-dualism is a metaphysical truth or a trick of perception, it forces us to reconsider the most basic assumptions about reality. If oneness is fundamental, then perhaps the quest to understand the universe isn't about decoding its parts, but recognizing that the parts were never really separate to begin with. Now, let's take this idea of oneness even further into the human brain itself. Recent neuroscience research reveals fascinating glimpses into how non-dual experiences might actually unfold in our minds. Take the phenomenon of ego dissolution, commonly reported during deep meditation or psychedelic experiences. People describe feeling as though the boundary between themselves and the world melts away, leaving only pure awareness without a sense of I. It's not just poetic description. Brain scans show something remarkable happening during these states. The default mode network, a web of brain regions linked to self-referential thinking, your inner monologue, memories, and sense of identity quiets down dramatically. This network usually keeps us anchored in our personal narratives, reinforcing the illusion of separation. But when its activity drops, as seen in studies on long-term meditators or under psilocybin, that rigid sense of self softens. Some researchers compare it to lifting a veil, revealing a more interconnected mode of perception. This isn't just subjective either. Mystical experiences triggered by meditation or psychedelics often share uncanny similarities across cultures and individuals. Reports of merging with the universe, timelessness, and a loss of ego that aligns strikingly with non-dual philosophy. Even more compelling, these experiences can lead to lasting changes in perspective. Participants frequently describe feeling more connected to others and less trapped by their individual worries, as if they've touched something deeper and more universal. Critics argue these are just altered brain states, not proof of metaphysical unity. But here's the twist: the very fact that our perception of separation can dissolve so completely suggests that individuality might be more fragile, more constructed than we assume. If the brain can shift from me versus the world to pure interconnectedness, does that hint at a fundamental reality beneath our usual filters? Whether you see this as neurological trickery or a glimpse behind the curtain, one thing's clear. The lines we draw between self and world may be far blurrier than they appear. Now, shifting our focus to the fabric of spacetime itself, let's explore a theory that reimagines reality as a dynamic, ever-changing puzzle. Causal dynamical triangulation proposes that spacetime isn't smooth and continuous as we often picture it, but instead is built from tiny, geometric building blocks called simplices. Think of them as the cosmic equivalent of Legos. These simplices, typically triangles or tetrahedrons in higher dimensions, fit together under strict rules, creating a structured yet flexible framework for the universe. At the heart of this idea is physicist Renate Loll and her team's groundbreaking work. They've shown how these simplices can evolve over time, following precise causal relationships to ensure events unfold in a logical order. No time loops or paradoxes here. What's especially clever about this approach is how it sidesteps the pesky singularities that plague other theories, like the infinite density at the center of black holes or the Big Bang itself. In this model, spacetime remains finite and well-behaved, even in extreme conditions, because the rules governing the simplices prevent runaway distortions. Imagine a universe where gravity isn't a force warping a smooth sheet, but emerges naturally from how these geometric pieces connect and interact. It's a radical departure from Einstein's classic view, yet it offers tantalizing solutions to long-standing puzzles. For instance, by treating time and space as discrete steps rather than a fluid continuum, the theory naturally incorporates quantum effects, bridging the gap between general relativity and quantum mechanics, a holy grail of modern physics. Critics point out that the math is fiendishly complex and experimental evidence remains elusive, but the elegance of causal dynamical triangulation lies in its ability to produce a universe that looks smooth and continuous at large scales, just as we observe, while revealing its pixelated nature only when you zoom in to the smallest possible levels. Whether this is the true architecture of reality or just another step toward a deeper theory, one thing's certain: it challenges us to think of spacetime not as a static stage but as a living, evolving structure. Now let's peel back another layer of this geometric universe. If spacetime is built from these tiny simplices, how does the four-dimensional reality we experience, 3 dimensions of space plus time, emerge from something simpler? Picture a mosaic where each tile is flat and two-dimensional, yet when you step back, the full image appears three-dimensional. Similarly, causal dynamical triangulation suggests our four-dimensional cosmos could arise from lower-dimensional building blocks like triangles or tetrahedrons, combining in just the right way to create the illusion of depth and time. This idea isn't entirely unique. It echoes themes from other cutting-edge theories like the Holographic Principle, where a two-dimensional surface encodes all the information of a three-dimensional space. Or string theory's landscape, where extra dimensions curl up so tightly they're invisible to us. But what sets causal dynamical triangulation apart is its insistence on causality, the strict rules that govern how these building blocks connect, ensuring time always flows forward and events unfold logically. Think of it like a flipbook animation. Individually, each page is just a static drawing, but when you flip through them rapidly, the illusion of motion emerges. In the same way, the dynamic interactions of these lower-dimensional simplices could give rise to the smooth, continuous spacetime we perceive. It's a reminder that reality might be far more modular and malleable than we've ever imagined. Critics might ask, if spacetime is truly built this way, where's the evidence? For now, it's mostly mathematical. But the tantalizing possibility remains that future experiments, perhaps probing the fabric of spacetime at incredibly small scales, could reveal hints of this pixelated architecture. Until then, this theory invites us to reconsider not just what reality is made of, but how complexity can emerge from astonishing simplicity. Now, let's shift our focus to a different angle on quantum reality, one where the act of observation isn't the key player. Enter objective collapse theories, which suggest that wave functions collapse on their own without any observer needed. Imagine a row of dominoes that topple spontaneously, not because someone pushed them, but because there's an inherent instability built into the system. That's the core idea here. Quantum states might collapse due to their own internal mechanics, not because we're looking at them. The most well-known version of this is the Garadi-Rimini-Weber, or GRW theory. It proposes that particles have a tiny but non-zero chance of suddenly localizing, snapping into a definite position without any outside interference. Over time, these random collapses add up, ensuring that large objects like cats or chairs never end up in the bizarre superpositions we see in the quantum world. It's nature's way of keeping the weirdness confined to the microscopic scale. This stands in stark contrast to the Copenhagen interpretation, where observation is the trigger for collapse, and the many worlds interpretation, where collapse never happens at all. Instead, every possibility branches into its own universe. Objective collapse theories offer a middle ground, saying reality doesn't need conscious observers to settle into a definite state. But here's the kicker: if collapses are happening on their own, why can't we detect them? Supporters argue that these collapses might leave subtle traces, like faint bursts of energy, which could one day be spotted in sensitive lab experiments. Others remain skeptical, pointing out that the theory adds an extra layer of complexity without any direct proof. Yet, the appeal is undeniable. It sidesteps the philosophical headaches of observer dependence while keeping quantum mechanics grounded in something tangible. So, is reality self-collapsing? The answer, for now, remains hidden in the quantum haze. Next up, we'll explore how scientists are trying to test these bold ideas in the lab, and whether they might finally crack the mystery of quantum collapse. Now, let's roll up our sleeves and dive into the real-world hunt for evidence. If objective collapse theories hold water, they should leave footprints, tiny but measurable signs in the fabric of reality. One tantalizing clue: X-rays. Supporters predict that when a wave function collapses spontaneously, it might release a minuscule burst of energy in the form of X-rays. Think of it like a quantum version of a camera flash, brief, faint, but potentially detectable. Researchers are now scanning ultra-cold materials and crystals for these elusive signals, hoping to catch nature in the act. But here's the catch: these X-rays would be incredibly weak, drowned out by background noise from cosmic rays or even everyday radioactivity. It's like trying to hear a whisper in a thunderstorm. Labs around the world, like the Gran Sasso facility in Italy, are tackling this challenge with shielded detectors cooled to near absolute zero. Yet so far, no smoking gun. Skeptics argue that the absence of evidence might just mean the theory's predictions are too subtle or simply wrong. What keeps objective collapse on the fringes isn't just the lack of data, though. It's the weight of Occam's razor. Why add an extra layer of spontaneous collapses when existing interpretations like Copenhagen or many worlds manage without them? For many physicists, the math should stay lean unless forced to grow. Still, the quest continues, driven by a stubborn question: what if reality isn't waiting for us to look? If future experiments spot those X-rays, it could rewrite quantum theory and our place in it. Up next, we'll shift gears to a theory that flips the script entirely, suggesting the universe itself might be a cosmic computer. Stay tuned. Now, let's step into a world where every particle we know has a hidden twin waiting to be discovered. This is the promise of supersymmetry, a theory that could solve some of the biggest mysteries in physics. The idea is elegant. For every known particle like electrons or quarks, there's a heavier superpartner or sparticle lurking just beyond our current reach. These sparticles could explain dark matter, unify the fundamental forces, and even tell us why the Higgs boson is so light. But here's the twist: despite decades of searching, the Large Hadron Collider hasn't found a single sparticle. The null results have left physicists scratching their heads. Some theories suggest these superpartners might be much heavier than expected, hiding just out of reach of our current colliders. Others propose workarounds like split supersymmetry, where only certain sparticles remain light enough to detect, while others are too massive to spot. The stakes are high. If supersymmetry is real, it could be the missing piece that ties quantum mechanics and gravity together. But if it's not, physicists may need to rethink some of their most cherished assumptions. The hunt continues, and with each experiment, we edge closer to uncovering whether the universe truly has this hidden symmetry, or if nature has a different surprise in store for us. Coming up, we'll explore how supersymmetry might connect to one of the cosmos' greatest enigmas, dark matter. Don't go anywhere. Now, let's peel back another layer of the supersymmetry mystery and see how it might hold the key to one of the universe's biggest puzzles, dark matter. If supersymmetry is real, its lightest particle, the neutralino, could be the perfect candidate for this invisible cosmic glue. Picture this: neutralinos don't interact with light or ordinary matter, making them ghostly and undetectable, just like dark matter seems to be. They'd be stable, lingering from the early universe, and their sheer numbers could explain why galaxies don't fly apart. But here's where things get thorny. Supersymmetry was originally proposed to solve the naturalness problem, why the Higgs boson's mass is so tiny compared to the enormous energies of the quantum world. The idea was that sparticles would cancel out extreme quantum fluctuations, keeping the Higgs light and elegant. Yet, if sparticles are too heavy to detect, as current LHC results suggest, that delicate balance falls apart. Critics argue this makes supersymmetry feel less natural, more like a patchwork fix than a fundamental truth. So where does that leave us? Some theorists are doubling down, tweaking supersymmetry models to keep neutralinos in play while sidestepping the naturalness issue. Others are eyeing entirely new ideas like actions or hidden dimensions. The beauty of science is in the chase. Every dead end forces us to think differently. Whether supersymmetry survives or not, the hunt for dark matter will keep pushing physics into uncharted territory. Next up, we'll warp into another mind-bending idea, brain cosmology, where our universe might just be one slice of a much larger cosmic loaf. Stay tuned. Now, imagine stepping into a world where our entire universe is just one thin layer floating in a vast, higher-dimensional space. This is the wild idea behind brain cosmology, which proposes that what we see as reality might actually be a three-dimensional membrane, or brain, drifting through a much larger, multidimensional expanse called the bulk. Picture it like a slice of bread in an endless cosmic loaf, except instead of bread, we're talking about entire universes stacked or floating in ways we can't even perceive. One of the most fascinating versions of this theory is the ekpyrotic model, which suggests that the Big Bang wasn't the beginning of everything, it was just a collision. According to this idea, our brain might have smashed into another parallel brain in the bulk, releasing an enormous amount of energy that kickstarted our universe as we know it. Think of it like two sheets of paper smacking together in midair, creating a burst of heat and motion. This collision wouldn't just explain the Big Bang, it could also account for why our universe appears so uniform, with energy spread evenly across space. But here's where it gets even weirder. If brains are real, there might be others out there, each with their own set of physical laws, particles, and even entirely different realities. Some theories suggest that gravity, unlike other forces, could leak into the bulk, which might explain why it feels so much weaker than electromagnetism or the nuclear forces. It's as if our universe is a ship floating on an ocean, and gravity is the water seeping through tiny cracks that we can't even see. Of course, brain cosmology isn't without its challenges. For one, we have no direct proof that extra dimensions or parallel brains exist. And while the math can be elegant, critics argue that the theory leans heavily on assumptions we can't yet test. But that's the thrill of theoretical physics. Sometimes the strangest ideas push us to rethink everything we thought we knew. Speaking of rethinking, our next theory takes us even deeper into the cosmic unknown, where reality itself might be nothing more than a giant quantum calculation. Stay curious because the journey's far from over. Now, let's take a closer look at one of the most puzzling quirks of our universe: gravity's surprising weakness. Compared to the other fundamental forces like electromagnetism or the strong nuclear force, gravity is incredibly feeble. Think about it. A tiny magnet can lift a paperclip, effortlessly defying the gravitational pull of the entire Earth. So why is gravity so much weaker than the other forces? Brain cosmology offers a fascinating explanation. The idea is that while most forces, like electromagnetism, are trapped entirely within our brain, gravity might have a unique ability to leak into the higher dimensional bulk. Imagine our universe as a sponge soaked with water. The water represents gravity, seeping out through tiny pores into the space around it. If gravity spreads out into extra dimensions we can't perceive, it would appear diluted in our three-dimensional world, almost as if it's been stretched thin across a hidden landscape. This could explain why gravity feels so weak compared to forces that stay tightly bound within our brain. But where exactly are these extra dimensions hiding? Some theories suggest they could be curled up into unimaginably small sizes, far tinier than even atoms. Picture a garden hose. From a distance, it looks like a simple one-dimensional line. But up close, you see it's actually a cylinder with a circular dimension wrapped around its length. If extra dimensions were curled up like this, they'd be too minuscule for us to detect with current technology. Yet their influence could still shape the behavior of gravity in ways we're only beginning to understand. Experiments like the Large Hadron Collider have searched for signs of these hidden dimensions, hoping to catch glimpses of particles that briefly escape our brain before snapping back. So far, no definitive evidence has been found, but the hunt continues. Whether or not these dimensions exist, the mere possibility challenges our understanding of reality itself. And that's what makes brain cosmology so thrilling. It dares us to imagine a cosmos far stranger than we ever thought possible. As we venture further, another theory waits just ahead, one where reality itself might be nothing more than an elaborate cosmic calculation. The mysteries only deepen from here. Stepping into another layer of reality's puzzle, let's explore how the fuzzy quantum world sharpens into the solid, predictable universe we experience every day. This is where quantum Darwinism comes in, a theory that bridges the gap between the weirdness of quantum mechanics and the stability of classical reality. At the heart of quantum Darwinism is the idea of pointer states. These are special quantum states that survive interactions with their surroundings while other states fade away. Imagine tossing a handful of fine sand into the wind. Most grains scatter, but a few stick to a nearby surface, leaving a clear imprint. In the same way, pointer states leave durable marks on their environment, while fragile quantum superpositions, those strange states where particles exist in multiple places at once, get wiped out. This process, called quantum decoherence, is why we don't see cats simultaneously alive and dead or chairs hovering in two places at once. But here's the twist: the environment isn't just a passive bystander. It actively selects which states become real for observers. Think of it like a cosmic game of telephone. As countless particles interact with a quantum system, they amplify certain information, the pointer states, while filtering out the noise. Over time, multiple observers measuring the same system will agree on its properties because they're all accessing these stable, environment-approved states. It's as if reality itself reaches a consensus through endless tiny conversations between particles. Quantum Darwinism doesn't just explain why the world looks classical, it also hints at why we perceive objects as having definite properties at all. Without this natural selection of quantum states, reality might remain a blur of probabilities. Yet mysteries linger. How much interaction is needed to solidify a pointer state? Could some quantum weirdness still slip through? As we peel back these layers, the line between the quantum and classical worlds grows even more fascinating. And just when you think reality can't get any stranger, another theory waits around the corner, ready to challenge everything we think we know. The journey is far from over. Now, let's take a closer look at a question that pushes quantum Darwinism into even deeper waters. What role does consciousness actually play in shaping reality? Some theories treat observers as passive recipients, simply reading out the pointer states that the environment has already selected. Others argue that observers might actively influence which states become real, blurring the line between measurement and creation. This debate leads us straight to the famous Wigner's friend paradox. Picture this: a scientist named Wigner conducts an experiment where his friend observes a quantum system inside a sealed lab. From the friend's perspective, the system collapses into a definite state the moment they measure it. But to Wigner outside the lab, the entire setup, friend included, remains in a quantum superposition until he checks. So, whose observation counts? Is reality fixed only when a conscious observer intervenes? Or does the environment do all the heavy lifting before anyone even looks? Quantum Darwinism offers a middle path. It suggests that while consciousness isn't required to collapse quantum states, the way we perceive reality is shaped by the environment's filtering process. In other words, the universe reaches consensus through countless interactions before we ever step in to observe. Yet, the paradox lingers. Could there be scenarios where conscious observation tips the scales? Some interpretations of quantum mechanics lean into this idea, while others dismiss it as unnecessary. The deeper we dig, the more we see how tangled the relationship is between mind and reality. Whether observers are passive witnesses or active participants, one thing's certain: quantum mechanics keeps us questioning the very nature of existence. And as we peel back these layers, another intriguing theory waits just ahead, ready to stretch our understanding even further. Now, stepping into a completely different realm of thought, let's explore a theory that challenges conventional science: morphic resonance. Proposed by biologist Rupert Sheldrake, this idea suggests that reality isn't just governed by fixed laws but is shaped by collective memory. Imagine a kind of invisible field that carries habits and patterns, influencing everything from crystal formation to animal behavior. The more a pattern repeats, the stronger it becomes in this field, making future repetitions easier. It's as if reality itself learns and evolves over time. Sheldrake's most famous example comes from experiments with rats. In one study, rats in London learned to navigate a maze faster over time. But here's the twist: rats in other parts of the world, with no connection to the first group, also seemed to learn the same maze more quickly, as if the knowledge was somehow spreading. Sheldrake argued this was evidence of morphic resonance, where the collective experience of earlier rats made the task easier for later ones. Skeptics, however, dismissed these results, pointing to flaws in experimental design or suggesting simpler explanations like selective breeding or improved lab techniques. The controversy doesn't end there. Mainstream science largely rejects morphic resonance, calling it pseudoscience for its lack of measurable mechanisms. Critics argue that without a way to detect or quantify these morphic fields, the theory remains untestable, a cardinal sin in the scientific method. Yet, Sheldrake counters that science has historically dismissed radical ideas before accepting them, from continental drift to quantum entanglement. Whether morphic resonance ever gains traction or fades into obscurity, it undeniably pushes us to question how rigid the so-called laws of nature really are. As we wrestle with these bold ideas, another layer of mystery waits just ahead, ready to challenge our understanding even further. Now, shifting our focus to the heart of the debate, let's examine why morphic fields clash so sharply with established scientific thought. At its core, this theory stands in stark contrast to the Platonic view of mathematics as the unchanging blueprint of reality. For centuries, many scientists and philosophers have embraced the idea that the universe operates according to eternal mathematical laws, fixed equations that don't evolve or adapt. Morphic resonance, on the other hand, suggests these laws might actually be more like habits shaped by accumulated experience over time. It's the difference between a rigid rulebook and a living, learning system. This tension reveals a fundamental divide in how we understand nature. Mainstream science favors precise, measurable forces like gravity or electromagnetism that can be tested, predicted, and replicated. Morphic fields, by their very nature, resist this approach. Without a clear way to detect or quantify them, skeptics argue the theory leans more into metaphysics than physics. It's not just about lack of evidence, it's about whether the idea fits the framework of how science traditionally defines what's real. Yet, Sheldrake's supporters counter that science has often expanded its boundaries to include once dismissed phenomena. Think of how quantum mechanics upended classical physics with its probabilities and uncertainties. Could morphic fields represent another paradigm shift, or are they a step too far into the speculative? For now, the scientific consensus holds firm, but the debate itself is a fascinating reminder that our understanding of reality is always, and perhaps should always be, up for revision. As we peel back these layers, another intriguing perspective awaits, one that blurs the line between the physical and the mathematical even further. Now, let's take a step back in time to revisit an idea once thought to be long forgotten: the concept of the ether. Before Einstein reshaped our understanding of space and time with relativity, scientists believed the universe was filled with an invisible medium called the luminiferous ether. This mysterious substance was thought to be the carrier of light waves, much like sound travels through air. But when experiments like Michelson-Morley failed to detect it, Einstein's theory of relativity seemed to bury the ether for good. Yet, like many ideas in science, the ether never truly disappeared. Modern physics has given it a new life, reimagining it through the lens of quantum vacuum energy. Picture empty space not as a void, but as a bubbling sea of virtual particles constantly appearing and disappearing. This quantum foam behaves remarkably like the old ether, a dynamic medium teeming with unseen activity. Some theorists even propose that this modern ether could hold the key to understanding dark energy, the mysterious force accelerating the expansion of the universe. The twist here is fascinating. While Einstein dismissed the need for a fixed ether to explain light's motion, his equations still allow for a flexible, dynamic version of it. Quantum field theory suggests that what we call empty space is anything but empty. It's a dense web of energy and potential. So, was the classical ether wrong, or was it just ahead of its time? The answer might lie somewhere in between, as science continues to uncover layers of reality that blur old distinctions. As we reconsider these age-old ideas with fresh eyes, another frontier of thought opens up, one that challenges even our most basic assumptions about the cosmos. Now, let's circle back to that pivotal moment in science when the Michelson-Morley experiment shook the foundations of physics. Their goal was simple: detect the ether by measuring changes in the speed of light as Earth moved through this hypothetical medium. But no matter how precise their measurements, they found nothing. No ether, no drag, no sign of the universal backdrop everyone expected. This null result became a turning point, paving the way for Einstein to declare that the ether simply wasn't necessary. His theory of relativity showed that light didn't need a medium to travel through. It could propagate perfectly well through the emptiness of space. Yet here's where things get intriguing. While Einstein dismissed the classical ether, quantum field theory later introduced something eerily similar: the Dirac sea. Picture this: a vast, invisible ocean of negative energy particles filling every corner of space. Though it sounds like science fiction, this concept helped explain phenomena like electron behavior and antimatter. In a way, the Dirac sea resurrected the spirit of the ether, not as a static stage for light, but as a dynamic, energetic substrate underlying reality. So, was Einstein wrong to discard the ether? Not exactly. He rejected a rigid, mechanical medium, but quantum physics revealed a subtler, more vibrant version of it. The Dirac sea, along with the quantum vacuum we discussed earlier, shows that space is far from empty. It's a seething, fluctuating arena where particles pop in and out of existence. This modern ether doesn't clash with relativity, it complements it, offering a deeper layer to the fabric of the universe. The lesson here is profound: sometimes old ideas don't die. They evolve, and as we peel back the layers of reality, we find that the past and present often intertwine in ways we never anticipated. Here's how entropy might be rewriting our understanding of time itself. The arrow of time, that one-way flow from past to future, has always been tied to the unstoppable rise of entropy. The universes slide into disorder. But what if quantum entanglement, that spooky connection between particles, is secretly driving the whole process? Picture two entangled particles instantly influencing each other no matter how far apart they are. Now imagine this happening on a cosmic scale. Every interaction, every measurement could be leaving a trail of quantum correlations that push entropy ever higher, like an invisible hand guiding time's arrow forward. This idea ties back to the past hypothesis, a puzzle that's haunted physicists for decades. Why did the universe start in such a ridiculously low entropy state, like a perfectly stacked deck of cards? One answer might lie in the Big Bang's quantum origins. If entanglement was woven into the fabric of the early universe, it could have set the stage for time's relentless march by creating those initial correlations. Think of it as the first domino tipping in a chain reaction that's still unfolding today. But here's the twist: if entanglement shapes time's arrow, could we ever reverse it? In theory, a universe where entanglement decreases over time might see entropy drop, making time flow backward. While that sounds like science fiction, it forces us to ask a deeper question. Is time's direction just a side effect of how quantum information spreads? The more we uncover, the clearer it becomes time might not be a fundamental feature of reality, but a ghostly echo of quantum connections we're only beginning to map. Now let's take this idea of time's arrow and flip it on its head. What if the future isn't just an outcome waiting to happen, but something that actively shapes the past? This mind-bending concept is known as retrocausality, and it challenges everything we think we know about cause and effect. One of the most intriguing pieces of evidence comes from the delayed choice experiments in quantum mechanics. Imagine shooting particles toward a screen through a barrier with two slits. If you measure which slit a particle goes through, it behaves like a single particle. But if you don't measure, it acts like a wave, creating an interference pattern. Here's the twist: what if you wait until after the particle has passed through the slits to decide whether to measure it? Astonishingly, the particle's behavior seems to change retroactively. as if the future measurement somehow reaches back in time to influence the past. This isn't just a quirky lab result, it hints at a deeper truth about reality. Physicist Yakir Aharonov proposed a radical framework called the two-state formalism, where particles exist in a kind of quantum handshake between past and future. In this view, quantum states aren't just determined by their history, but also by their future interactions. It's as if the universe is playing a cosmic game of chess where moves are made backward and forward at the same time. So does the future really affect the past? The math suggests it might, at least in the quantum realm. While this idea defies common sense, it forces us to rethink the very nature of time. Maybe causality isn't a one-way street after all, but a tangled web where past, present, and future are far more connected than we ever imagined. But here's where things get even more fascinating. Let's step into a perspective that dissolves the boundary between mind and matter entirely: neutral monism. This theory, championed by philosophers like Bertrand Russell and William James, suggests that reality isn't split into two separate realms, mental and physical, but is instead made of a single, neutral substance that manifests as both. Think of it like a coin. Heads and tails are different, but they're still part of the same object. Neutral monism offers a refreshing alternative to dualism, which treats mind and body as distinct, and materialism, which reduces everything to physical matter. Instead, it proposes that what we call mental and physical are just two ways of describing the same underlying reality. Quantum mechanics lends a curious metaphor here. Just as particles can behave as both waves and particles depending on how you observe them, perhaps consciousness and matter are two sides of the same cosmic coin. Russell argued that our perceptions aren't representations of an external world, but are the world itself, woven from the same fabric. James took it further, suggesting that pure experience is the foundation of reality, with no need for dividing lines. This idea resonates with modern panpsychism, where even atoms might harbor a rudimentary form of awareness. So, is the universe neither purely mental nor purely physical, but something deeper that gives rise to both? Neutral monism invites us to consider that the dichotomy we take for granted might be an illusion, a story we tell ourselves to make sense of a far more unified cosmos. Now, let's bring neutral monism into the modern era with a twist: David Chalmers' idea of panpsychism. This theory takes the unified reality suggested by neutral monism and adds a bold layer. What if the building blocks of the universe aren't fully conscious but contain the seeds of consciousness? Chalmers suggests that even the most basic particles have properties that, when combined in the right way, give rise to subjective experience. It's like saying flour, water, and yeast aren't bred on their own, but together they create something entirely new. Panpsychism tackles the infamous, hard problem of consciousness, the mystery of how and why physical processes in the brain produce inner experience. Unlike traditional materialism, which struggles to explain why we feel anything at all, this approach sidesteps the issue by proposing that experience isn't something that magically emerges from complexity. Instead, it's woven into the fabric of reality from the start, just waiting to be organized. Critics argue that this still leaves gaps. How do these proto-conscious properties actually combine? But supporters counter that it's no more mysterious than other fundamental forces like gravity. After all, we accept that mass bends space-time without fully understanding why. Could consciousness be just as foundational? By blending neutral monism with panpsychism, Chalmers offers a compelling middle ground, one where mind and matter aren't separate but spring from the same deep, enigmatic source. So, does reality fundamentally hum with the potential for consciousness, even in its simplest forms? The answer might reshape not just how we see ourselves, but the very nature of existence. Turning our attention to flow and structure, let's explore Adrian Bejan's constructal law, a theory that suggests everything in the universe organizes itself to move energy more efficiently. Picture a river carving its path. It doesn't twist randomly but follows the route of least resistance, shaping the landscape over time. Brains argues this isn't just geology, it's a universal principle. From the branching veins in a leaf to the sprawling networks of highways, nature and human design alike seem to obey this hidden rule of flow optimization. What's fascinating is how this law bridges scales. On a cosmic level, galaxies distribute matter in intricate webs, almost like giant versions of river deltas. Social systems, too, evolve to streamline movement. Think of how cities organically develop subway lines or how information cascades through viral trends. The constructal law frames these patterns not as coincidence but as inevitable outcomes of a deeper drive toward efficiency. Critics question whether this is a true law or just an observation of emergent behavior. But supporters point to its predictive power. Engineers use it to design better cooling systems, and ecologists apply it to understand animal migration. If reality truly self-organizes to optimize flow, it hints at a universe that's less chaotic and more computationally elegant than we might assume. So, is the constructal law a master key to understanding complexity? Whether in the swirl of a galaxy or the pulse of a city, the answer might lie in how things find their way. Now let's take this idea even further. What if the constructal law doesn't just describe life but actually predicts its inevitability? Adrian Brains himself has suggested that the drive toward flow optimization might be why life exists in the first place. Think about biological systems. A single cell is a masterclass in efficiency, with membranes and organelles arranged to move nutrients and waste with minimal effort. Over billions of years, evolution seems to have followed the same script, streamlining organisms to better channel energy, from the fractal branching of lungs to the helical structure of DNA. But here's the big question: does this mean life had to emerge, or is the constructal law simply observing patterns after the fact? Some scientists argue that if a universe favors efficient flow, then self-replicating systems like life are almost a mathematical certainty. Others push back, calling the law a useful metaphor rather than a fundamental force. After all, lightning bolts and river deltas don't reproduce or adapt, they just follow physics. Yet there's a tantalizing middle ground. Researchers point to how lifelike processes like crystal growth or chemical oscillations mimic biological efficiency without being alive. If the universe naturally trends toward these flow-friendly structures, could life be an extreme extension of that principle? Whether the constructal law is a cosmic blueprint or just a clever lens, one thing's clear: the line between the living and non-living might be thinner than we think. So where does that leave us? Perhaps the real takeaway isn't just about life, but about a universe that seems wired to find the easiest path, whether in a leaf, a galaxy, or even you. Now let's shift our focus to something that feels like it's straight out of science fiction, but might be closer to reality than we think: the idea of digital consciousness. Imagine a world where your mind, with all its memories, thoughts, and emotions, could be uploaded into a computer. This isn't just the plot of a futuristic movie, it's a serious theory gaining traction among scientists and futurists. The concept is called whole brain emulation, where every neuron and synapse in your brain is meticulously mapped and replicated in a digital format. The result: a digital version of you that could think, feel, and even exist indefinitely inside a machine. But here's where things get tricky. If your mind is copied into a computer, is that digital version truly you? Or is it just a flawless imitation? This is the identity paradox at the heart of digital consciousness. Some argue that as long as the copy thinks and acts exactly like you, it is you. Others counter that no matter how perfect the replication, the original you still exists separately, raising unsettling questions about which version is the real one. And what happens if multiple copies are made? Would each one have its own independent consciousness? The ethical dilemmas are just as mind-bending. If digital minds can experience emotions, do they deserve rights? Could they suffer if trapped in a virtual world? And what about the risk of abuse? Could someone exploit or even delete a digital consciousness? Philosophers and technologists are already wrestling with these questions because the line between human and artificial mind might one day blur beyond recognition. Yet, for all the uncertainties, the potential is staggering. Digital consciousness could offer a form of immortality, allowing people to live long after their biological bodies fail. It could revolutionize space exploration, sending human minds to distant stars without the limitations of fragile human bodies. Or it could create entirely new forms of intelligence, merging human creativity with machine precision. So, as we stand on the brink of this uncharted territory, one thing is certain. The idea of digital consciousness forces us to rethink not just technology, but what it means to be human at all. And with that, we're ready to dive deeper into the counterarguments because every radical idea deserves a fair debate. Now, let's pause and consider a powerful counterargument to digital consciousness, one that challenges whether a machine could ever truly understand in the way humans do. This comes from philosopher John Searle and his famous Chinese room thought experiment. Picture this: a person sits alone in a room with a massive rulebook written in English. Through a slot in the door, they receive notes with Chinese characters, a language they don't understand. By following the rulebook, they can match incoming symbols with the correct responses and send back perfectly coherent replies in Chinese. To someone outside, it would seem like the person inside knows Chinese. But in reality, they're just mechanically following instructions without any genuine comprehension. Searle's point: even if a computer mimics human-like responses just like the person in the room, that doesn't mean it actually experiences thoughts, feelings, or understanding. This strikes at the heart of strong AI, the idea that a perfectly programmed machine could possess real consciousness. Instead, Searle argues, computers might just be incredibly sophisticated symbol manipulators, processing inputs without any inner awareness. This leads us to a deeper question: is biological uniqueness essential for consciousness? Supporters of biological naturalism insist that human minds aren't just software running on the hardware of the brain, they're inseparable from the living, organic processes that create them. Think of it like fire. You can't replicate the essence of fire just by simulating its glow and heat on a screen. Similarly, could consciousness emerge only from the messy, chemical dance of neurons? Yet, critics of Searle's argument highlight a loophole. What if the entire system, not just the person in the room, understands Chinese? The room, the rulebook, and the person working together might collectively achieve something the individual parts can't. Apply that to AI, and perhaps consciousness arises from the complexity of interactions, not just isolated components. So where does that leave digital consciousness? If Searle is right, uploading minds might create flawless imitations, brilliant puppets with no inner light. But if the system itself can birth awareness, the digital you might be just as real as the original. It's a debate that forces us to confront the most elusive mystery of all: what is the spark of consciousness? And as we'll see next, the answers might reshape not just technology, but our very sense of self. Now, let's unfold another fascinating perspective, one that suggests reality might be far more interconnected than it appears. This is David Bohm's theory of the implicate order, a radical idea proposing that beneath the surface chaos of our everyday world lies a deeper, hidden harmony. Bohm, a quantum physicist and philosopher, argued that the universe operates like an unbroken whole, where everything is secretly woven together in what he called the implicate or enfolded order. Think of it like a hologram. If you cut a piece off a holographic film, the entire image is still contained in that fragment, just in a more subtle, compressed form. Similarly, Bohm believed every part of the universe contains the whole in some way, with all aspects of reality continuously unfolding and enfolding back into this deeper fabric. But what about the messy, separate world we see? Bohm called that the explicate order, the unfolded, visible layer we interact with daily. He saw it as a kind of projection from the implicate background, much like how a hologram reconstructs a three-dimensional image from a flat surface. This wasn't just poetic speculation. Bohm was tackling one of quantum mechanics' biggest puzzles, non-locality, the eerie phenomenon where particles instantly influence each other across vast distances, as proven by experiments testing Bell's theorem. For Bohm, this spooky action at a distance made perfect sense if particles weren't truly separate, but were ripples emerging from the same hidden ocean of implicate reality. His theory also revived the idea of hidden variables, invisible factors that might determine quantum outcomes, countering the mainstream view that particles have no definite properties until measured. While most physicists dismissed hidden variables as unnecessary, Bohm's version wasn't about restoring old-school determinism. Instead, he envisioned a dynamic, flowing reality where cause and effect weren't linear but woven into a vast participatory dance. Critics argue that the implicate order is more philosophy than testable science, but its echoes persist. Some interpretations of quantum gravity and string theory flirt with similar holism, and the holographic principle we explored earlier shares Bohm's intuition that information might be fundamentally unified. So next time you feel like the world is fragmented, remember Bohm's vision. Beneath the surface, everything might already be connected. And as we'll see, this idea of cosmic unity takes even stranger turns when we explore the role of consciousness itself. Building on Bohm's vision of an interconnected universe, let's explore how his ideas challenge one of science's most deeply held assumptions, reductionism. For centuries, the dominant approach has been to break reality down into smaller and smaller parts, believing that by understanding the pieces we can grasp the whole. But Bohm's implicate order flips this logic on its head. Instead of seeing the universe as a machine built from separate cogs, he proposed that wholeness comes first, and what we perceive as fragments are just temporary expressions of a deeper unity. This clash between wholeness and fragmentation isn't just philosophical. It reshapes how we interpret quantum mechanics. Take the famous double-slit experiment, where particles behave like waves unless observed. Reductionist explanations often treat this as a puzzle to be solved by analyzing the particle's properties. But for Bohm, the phenomenon makes perfect sense if we consider the particle as part of an unbroken field, the quantum potential guiding its motion in ways that defy classical logic. Interestingly, Bohm's ideas have found new life in the revival of pilot wave theory, an alternative to mainstream quantum mechanics. Originally proposed by Louis de Broglie in the 1920s, this theory was sidelined for decades but has recently gained fresh attention. Pilot wave theory suggests particles aren't probabilistic clouds but have definite positions, guided by a pilot wave that orchestrates their behavior. Sound familiar? It's a close cousin to Bohm's hidden variables, offering a deterministic yet non-local picture of reality. Critics of Bohm and pilot wave theories argue they add unnecessary complexity. Why invoke hidden waves or implicate orders when standard quantum mechanics works just fine? But supporters counter that these frameworks restore something crucial: intelligibility. In a Bohmian universe, quantum weirdness isn't just accepted as random magic. It's a window into a deeper, more coherent reality where everything is subtly intertwined. So where does this leave reductionism? It's not that breaking things down is useless, it's just incomplete. Bohm's legacy reminds us that while fragmentation helps us analyze, wholeness might be the key to truly understanding. And as we'll see next, this tension between the parts and the whole takes us even deeper into the mysteries of consciousness and reality itself. Now, let's step into a world where time itself bends to the rhythm of consciousness. Unlike the static block universe we've explored before, where past, present, and future exist all at once, philosophers like Henry Bergson and Alfred North Whitehead argued that time flows because we experience it flowing. To them, time isn't just a dimension on a cosmic spreadsheet, it's an active, dynamic force shaped by perception. Bergson called this duration, the idea that time isn't just a series of separate moments but a continuous, indivisible stream. Think of it like listening to a melody. You don't hear individual notes in isolation. You feel the music as a whole where each note blends into the next. Bergson believed reality works the same way our consciousness stitches moments together, creating the illusion of movement. Whitehead took this further, suggesting that the universe is a process, not a collection of objects. Every instant is a new occasion of experience, where reality literally unfolds through perception. This clashes starkly with the block universe view, where Einstein's relativity paints time as a frozen landscape. If you've ever felt like time speeds up when you're excited or drags when you're bored, Bergson and Whitehead would say that's not an illusion, it's proof that time is deeply personal. Even neuroscience hints at this. Our brains don't process time like a clock, they warp it based on attention, emotion, and memory. Ever notice how childhood summers felt endless but years now blur together? That's subjective time flow in action. Critics argue this makes time hopelessly vague. If it's all in our heads, how do we explain the universe's consistent laws? But supporters counter that physics alone can't capture the lived experience of time. After all, entropy and quantum mechanics might set the stage, but consciousness is the actor bringing the drama to life. So, is time a river we're swept along in, or a road we're standing on? The debate isn't just philosophical, it reshapes how we understand memory, free will, and even the nature of reality itself. And as we'll soon see, this idea of time as a mental construct leads us to an even stranger possibility, that the present moment might not be as solid as it feels. Now, let's peel back another layer of this temporal puzzle. How exactly does our brain weave individual moments into what feels like a smooth, unbroken stream of time? This brings us to the concept of the specious present, a term coined by psychologist William James to describe the brief window where our brain stitches together sensory input to create the illusion of a continuous now. Think of it as a magician's trick where the brain takes snapshots and blends them so seamlessly that we never notice the gaps. Neurologically, this happens because our perception isn't instant. It takes time for sensory data to travel through neurons, getting processed and integrated. Research suggests the specious present lasts about 2 to 3 seconds, just long enough to hear a sentence, recognize a face, or hum a tune. Outside that window, memories fade into the past and anticipation nudges us toward the future. But here's the twist, even this present is slightly outdated. By the time you're aware of an event, your brain has already been working on it for milliseconds. Enter Benjamin Libet's famous experiments, which threw a wrench into our understanding of free will. Libet found that brain activity predicting a simple action like pressing a button occurs before we're consciously aware of making the decision. In other words, your brain might already be gearing up to act before you feel like you've chosen to do it. This delay suggests that what we call the present is more like a carefully edited highlight reel, a reconstruction after the fact. Critics argue this doesn't erase free will, but highlights how consciousness lags behind the subconscious machinery of the brain. Yet it raises eerie questions. If our experience of now is a post-production edit, how much of reality are we missing in real time? And if time flow is just a brain-built illusion, could other aspects of reality be too? This blurry boundary between perception and objective time leads us even deeper into the rabbit hole, toward theories where consciousness doesn't just observe reality but actively shapes it. Now, let's dive into a theory that flips our understanding of reality on its head: biocentrism. Proposed by scientist Robert Lanza, this bold idea suggests that life isn't just a passive observer of the universe, but the very force that creates it. Imagine a cosmic painter, and consciousness is the brush shaping reality stroke by stroke. At the heart of biocentrism is the idea that space and time aren't fixed, external structures, but tools our minds use to make sense of experience. Lanza draws a surprising parallel to quantum mechanics, where particles only settle into definite states when observed. Could it be that reality itself is waiting for consciousness to collapse it into existence? This echoes the famous double-slit experiment, where light behaves as both a wave and a particle until someone tries to measure it. But biocentrism goes further, tying into the universe's eerie fine-tuning. Why do the laws of physics seem perfectly calibrated for life to exist? Lanza argues it's no accident we're not just lucky beneficiaries of a hospitable cosmos. Instead, life and reality are intertwined in a dance where one can't exist without the other. Without consciousness, the universe might be nothing more than a fog of probabilities, lacking any definite form. Critics push back, of course. Some say biocentrism leans too heavily on philosophical speculation, blending science with metaphysics. Others point out that the universe existed long before life arose, so how could consciousness have been there to create it? But Lanza counters with a multiverse twist. Perhaps every possible universe exists in parallel, and consciousness simply tunes into the one we perceive. This theory leaves us with a dizzying question. If reality depends on life, what happens when life ends? Could the universe dissolve like a dream upon waking? Or does consciousness somehow persist, reshaping existence beyond biology? It's a radical reimagining of our place in the cosmos, one where we're not just passengers but co-creators of everything we see. Turning to an even more mind-bending implication of biocentrism, what if consciousness doesn't just shape reality but outlasts it? If time and space are truly constructs of the mind, as Lanza suggests, then death might not be the end we assume. Imagine consciousness like a radio signal tuning into different frequencies of reality. When the biological body stops functioning, could that signal simply switch channels, persisting in a realm beyond our familiar dimensions? Near-death experiences, where people report vivid awareness even when clinically dead, offer tantalizing but controversial glimpses into this possibility. Testing biocentrism scientifically, however, remains a formidable challenge. Unlike theories that predict measurable particles or cosmic phenomena, biocentrism deals with the fabric of perception itself. Some researchers propose experiments at the quantum level, like observing whether conscious observation alters decay rates in radioactive materials. Others look to advanced brain studies, probing whether neural activity truly generates consciousness or merely filters it from a deeper, non-physical source. Yet critics argue that without concrete predictions or falsifiable evidence, biocentrism straddles the line between science and philosophy. Can a theory that places consciousness at the center ever be proven, or does it risk becoming an untestable loop? Lanza's supporters counter that dismissing it for lacking traditional proof might be missing the point after all. If reality is observer-dependent, then the tools of observation themselves could be part of the illusion. This leaves us straddling two worlds, one where science demands hard data, and another where the very nature of data might be a mental construct. Whether biocentrism ever moves from speculation to settled theory, it undeniably reshapes how we ponder life's ultimate questions, not just how we exist, but why existence feels real at all. Shifting our gaze to another radical perspective, let's explore the participatory anthropic principle, a theory that flips the script on reality itself. Proposed by physicist John Wheeler, this idea suggests the universe doesn't just exist independently. It requires conscious observers to bring it into being. Think of it like a cosmic version of if a tree falls in the forest. Wheeler argued that reality remains undefined until an observer interacts with it, weaving the universe into existence through the very act of perception. One of the most striking pieces of evidence for this comes from quantum mechanics, specifically the delayed choice experiment. Imagine a particle's path being altered retroactively, not by something in the present, but by a decision made after the particle's journey seems complete. This bizarre phenomenon hints that observation doesn't just measure reality, it might create it, tying back to Wheeler's famous phrase, "it from bit." Here, bit refers to the fundamental units of information, suggesting the universe could be built not from matter or energy, but from the answers to yes or no questions posed by observers. But what does this mean for the cosmos as a whole? If observers are necessary to crystallize reality, does the universe exist in a fuzzy, half-formed state until life emerges to perceive it? Some theorists take this further, proposing that the fine-tuning of physical constants, those precise values that allow life to exist, isn't a coincidence, but a consequence of observation. In other words, the universe is tailored for observers because without them, it wouldn't fully manifest. Critics, of course, raise eyebrows. They argue this veers perilously close to solipsism, the idea that only one's mind is sure to exist, and question whether it's science or metaphysics. Yet supporters counter that quantum mechanics already blurs the line between observer and observed, making Wheeler's principle less a leap of faith and more an extension of established physics. Whether you find it inspiring or unsettling, the participatory anthropic principle forces us to reconsider our place in the cosmos. Are we merely bystanders in a pre-existing universe or active participants in its very creation? The answer might lie somewhere in the quantum haze, waiting for the next observation to bring it into focus. Now, let's dig deeper into one of the most heated debates sparked by the participatory anthropic principle, the fine-tuning of the universe. Why do the fundamental constants of nature, like the strength of gravity or the mass of an electron, have such precise values that allow life to exist? Some scientists argue this isn't luck at all, but evidence of something deeper. On one side, proponents of the multiverse theory suggest our universe is just one of countless others, each with different physical laws. In this vast cosmic lottery, it's no surprise that at least one universe ours ended up with the right numbers for life. Think of it like rolling a die an infinite number of times. Eventually, you'll land on the perfect combination. This idea sidesteps the need for intentional fine-tuning by appealing to sheer probability. But others find this unsatisfying. They propose an alternative. What if the universe's life-friendly constants hint at some form of design? Not necessarily a divine architect, but perhaps an underlying principle or self-organizing mechanism that naturally leads to complexity. Some even tie this back to the participatory anthropic principle, suggesting observers play a role in shaping these constants through the act of measurement itself. Skeptics, of course, push back. They argue that invoking a multiverse merely kicks the problem down the road. What, after all, determines the rules governing those universes? Meanwhile, design explanations risk venturing into untestable territory, blurring the line between science and philosophy. Yet the debate rages on because the stakes are so high. If the multiverse is real, it rewrites our understanding of existence. If some form of design is at work, it challenges the very nature of reality's origins. Either way, the fine-tuning problem forces us to confront a humbling question. Is our universe a fluke, or is there something more profound at play? The answer, much like quantum superposition, remains unresolved until we take a closer look. Now, let's shift gears to a radically different take on reality, one where the universe operates like a vast, self-running computer program. This is the cellular automaton universe theory, which suggests that everything around us, space, time, even consciousness, might just be the output of simple, pixel-like rules playing out on a cosmic scale. The idea traces back to pioneers like Konrad Zuse, who proposed that the universe could be a giant digital computation, and Stephen Wolfram, who explored how complex behavior can emerge from basic algorithmic rules. Imagine the universe as a grid where each cell follows a tiny set of instructions, like turn on if your neighbor is off. Over time, these simple interactions could generate the staggering complexity we see, from galaxies to human thought. One of the most mind-bending aspects of this theory is computational irreducibility, the notion that some processes can't be shortcut or predicted without running every step. Even if the universe's rules are simple, their outcomes might be fundamentally unknowable in advance. It's like trying to guess the ending of a movie by only reading the first scene. The only way to know is to watch it unfold. Yet this raises a tantalizing question. If reality is algorithmic, could free will exist? Some argue that unpredictability doesn't equal freedom, while others see it as proof that novelty and creativity are baked into the system. Either way, the cellular automaton theory forces us to reconsider whether the universe is a machine, an art project, or something stranger still, a game with rules we're only beginning to decode. Up next, we'll explore how this digital lens might reshape our understanding of choice itself. Could free will be an illusion, or is there room for agency in a rule-bound cosmos? The answer might lie in the gaps between the pixels. Now, let's tackle the big question looming over the cellular automaton universe. Does free will have any place in a reality governed by strict, unbreakable rules? If every event is just the result of pixel-like cells following pre-programmed instructions, where does human choice fit in? Some argue that algorithmic determinism leaves no room for genuine freedom. After all, if the universe is a cosmic clockwork, then every decision you think you're making was already set in motion by the initial conditions of the grid. But here's where things get fascinating. Even in a rule-bound system, complexity can give rise to something that feels remarkably like free will. Take emergent novelty, the idea that simple rules can produce unpredictable, never-before-seen patterns. Think of how a handful of musical notes can combine into infinite melodies. In the same way, the interactions of cosmic cells might spawn behaviors so intricate that they create the illusion, or perhaps the reality, of choice. This tension between determinism and creativity isn't just philosophical. It echoes debates in neuroscience, where some scientists argue that our brains operate like biological algorithms, while others point to quantum processes or chaotic systems as loopholes for agency. Either way, the cellular automaton theory doesn't just challenge our view of the universe, it forces us to redefine what it means to make a decision. Is free will simply the universe's way of surprising itself? Next up, we'll dive into an even stranger thought experiment, one where your consciousness might be the only thing that's real. Stay tuned as we explore quantum immortality, a theory that turns survival into a cosmic game of chance. Shifting gears to a mind-bending twist on survival, let's explore quantum immortality, a theory that suggests your consciousness might never experience death. Picture this: in the many worlds interpretation of quantum mechanics, every possible outcome of an event spawns a new universe. Now, imagine you're the subject in a twisted version of Schrödinger's cat experiment. If a device has a 50% chance of ending your life, the many worlds interpretation says both outcomes happen, just in separate branches of reality. In one world, you're gone, but in another, you survive. And here's the eerie part: your conscious experience would only continue in the worlds where you're alive. This isn't just about dodging bullets or surviving accidents. It implies that from your perspective, you'd always find yourself in a universe where you somehow endure, no matter how unlikely the odds. Critics call this a cosmic sleight of hand, a trick of probability where consciousness cherry-picks the favorable timelines. But supporters argue it's a logical extension of quantum branching. After all, if every decision creates new worlds, why wouldn't your awareness follow the path where it persists? The theory doesn't promise invincibility, though. It just suggests that death might be something you never personally witness. Whether that's comforting or terrifying depends on how you view the multiverse. Up next, we'll weigh the ethical and logical dilemmas this raises, like whether quantum immortality could turn life into a reckless game of chance. Now let's untangle the ethical knots this theory creates. If quantum immortality means your consciousness only experiences timelines where you survive, does that make reckless behavior justifiable? Some might see it as a green light to take extreme risks, assuming they'll always land in a universe where they live. But here's the catch. While you might never perceive death, the people around you would still witness your demise in countless branching realities. The grief and consequences in those worlds don't just vanish, they're part of the multiverse's fabric too. And what about the logic behind it? Quantum immortality hinges on the idea that consciousness follows survival, but it doesn't account for aging or natural limits. Unlike Boltzmann Brains, those random, self-aware blips in the void that briefly flicker into existence, your longevity isn't infinite. You might dodge fatal accidents, but time still marches on. Eventually, biology catches up, leaving you with a haunting question. Does quantum immortality just delay the inevitable, or is there a universe where you somehow cheat entropy itself? The contrast between these theories is stark. Boltzmann brains are lonely flukes, here and gone in an instant, while quantum immortality suggests a strange kind of persistence. But both force us to confront the same unsettling truth. Reality might not be as solid or as singular as we think. Whether that's liberating or unnerving, one thing's certain: it turns the simplest choices into cosmic dilemmas. Now let's shift our perspective to something even more abstract: the idea that mathematics isn't just a human invention, but the very foundation of reality itself. This is the core of the Platonic mathematical universe theory, championed by physicist Max Tegmark. He argues that numbers, equations, and geometric shapes exist in a timeless, unchanging realm, completely independent of human thought. Think of it like this: the Pythagorean theorem wasn't created when Pythagoras wrote it down. It was always true, waiting to be discovered. In this view, the universe isn't just described by math, it is math. Tegmark takes this even further with his Level 4 multiverse, a staggering idea that every mathematically possible structure exists somewhere in the cosmic landscape. If an equation can describe a universe with different laws of physics or even entirely new dimensions, then that universe is real, floating in an infinite sea of mathematical possibilities. Some might be lifeless voids, others could be teeming with complexity beyond our imagination. The unsettling implication: our universe is just one page in a boundless mathematical library, with no special significance beyond the fact that we're here to observe it. Critics push back, asking, if math is so fundamental, why does it sometimes feel invented rather than discovered? Why do certain equations seem elegant or arbitrary? But Tegmark counters that these are just limitations of human perception, like ants trying to comprehend the internet. Whether this theory leaves you awestruck or skeptical, one thing's undeniable: it makes our reality feel less like a cosmic accident and more like an inevitable piece of something infinitely grander. And with that, we're ready to dive even deeper into the rabbit hole, where math might not just describe the universe but be the universe. Now let's untangle one of the biggest puzzles in the Platonic mathematical universe: whether math is something we invent or simply uncover. This debate stretches all the way back to the ancient Pythagoreans, who saw numbers as divine, almost mystical truths waiting to be revealed. Fast forward to the 20th century, and logician Kurt Gödel delivered a bombshell with his incompleteness theorems. He proved that even in the most rigorous mathematical systems, there will always be true statements that can't be proven within the system's own rules. For some, this suggests math has an objective reality beyond human logic, like chiseling away at a statue already hidden in the stone. Others argue math is a human-made toolkit evolving to solve problems. The number 0, for example, didn't exist in ancient Greek math. It was invented out of necessity. So is math the eternal language of the cosmos, or just a really useful fiction? Tegmark's camp leans hard toward discovery. They point to phenomena like fractal patterns in nature or the uncanny precision of physics equations. Why would invented rules fit the universe so perfectly? Skeptics fire back. Maybe we're just biased to notice the patterns that match our tools. The twist: this isn't just philosophy. If math is discovered, it hints at a deeper layer of reality. If it's invented, then our universe might be stranger than we ever imagined. Either way, the question keeps mathematicians and physicists awake at night, and with good reason. Next up, we'll explore how these ideas collide with one of the wildest origin stories of all, a universe popping into existence from pure nothingness. Now, let's shift gears to one of the most mind-bending ideas about how everything began: the theory of vacuum genesis. Picture this: the entire universe, all the galaxies, stars, and even you, might have sprung into existence from absolute nothingness. Not empty space, but true nothingness. No time, no matter, no energy. How quantum fluctuations, at the tiniest scales, even a perfect vacuum isn't truly empty. It's a seething foam of potential where particles and antiparticles blink in and out of existence. Physicist Edward Tryon first suggested that our universe could be one of these random fluctuations, just on a cosmic scale. Imagine a bubble of spacetime popping into being, riding a wave of quantum uncertainty. Lawrence Krauss took it further, arguing that nothing is unstable. In quantum physics, nothing isn't peaceful. It's a chaotic dance of probabilities. Given enough time or no time at all, depending on how you see it, a fluctuation could tip the scales, birthing a universe. No divine spark, no grand collision, just raw quantum chance. Critics ask, how can nothing have properties like quantum fields? But supporters counter that even nothing might obey physics we don't yet understand. After all, if the universe has a net energy of zero balancing positive matter with negative gravity, then maybe it really is the ultimate free lunch. Up next, we'll see how this ties into ancient ideas of creation, and whether nothing might just be the most fertile ground of all. Let's take this idea one step further. If nothing can give rise to everything, why is there something rather than nothing at all? This isn't just a physics question, it's one of philosophy's oldest puzzles. Think about it. For the universe to emerge from a quantum fluctuation, nothing must have some inherent instability, some hidden potential bubbling beneath the surface. Lawrence Krauss argues that nothing in quantum terms isn't empty. It's a restless, dynamic void where particles flicker in and out of existence. Given enough time, or perhaps outside of time entirely, one of these fluctuations could have tipped the balance, birthing our universe. But here's the twist: this idea isn't entirely new. Ancient Hindu and Buddhist cosmologies describe creation in startlingly similar ways. The Rig Veda, one of Hinduism's oldest texts, speaks of a primordial void, a state of nothingness that paradoxically contains the seed of everything. Buddhist philosophy takes it further, suggesting that existence and emptiness are two sides of the same coin, a concept eerily reminiscent of quantum foam's particle-antiparticle pairs. Critics push back, questioning whether nothing can even have properties like quantum fields or fluctuation probabilities. If nothing is truly nothing, how can it produce something? But proponents counter that our human intuition about nothing might be flawed. What we call nothing could be a rich, structured ground from which reality naturally emerges. So, is nothing the final answer, or just a placeholder for deeper physics we don't yet understand? Maybe the real mystery isn't why there's something, but why we ever assumed there could be nothing at all. Next, we'll dive into another radical idea: whether our universe is just one of countless bubbles in an endless cosmic sea. But before we leave the quantum realm behind, let's explore a theory that ties it all back to the most mysterious phenomenon of all: consciousness itself. Enter ORCH, or the idea that your mind might be running on quantum computations happening deep inside your brain cells. Proposed by physicist Roger Penrose and anesthesiologist Stuart Hameroff, This theory suggests that consciousness arises from tiny structures called microtubules, protein filaments inside neurons. These microtubules, they argue, aren't just cellular scaffolding, they're quantum computers. According to Orch, or when these microtubules perform quantum calculations, the collapse of their wave functions generates moments of awareness. Here's where it gets even stranger. Anesthesia might hold the key to testing this. Why do anesthetic gases turn off consciousness? Hameroff argues it's because they disrupt those delicate quantum processes in the microtubules. Supporters point to studies showing that anesthetics affect microtubule stability, hinting at a deeper link. But critics aren't convinced. Many physicists argue that the brain is simply too warm and noisy for fragile quantum states to survive long enough to matter. Decoherence, the breakdown of quantum effects, would wipe out these processes almost instantly. Others say the theory leans too heavily on mystery, using quantum physics as a placeholder for what we don't yet understand about the mind. Yet, Orch refuses to fade away. Recent research in quantum biology, like how birds navigate using quantum effects in their eyes, suggests nature might indeed exploit quantum phenomena in warm, wet environments. Could our brains be doing the same? Whether Orch is a groundbreaking insight or a beautiful dead end, one thing's certain: it forces us to rethink where consciousness truly begins. And that brings us to our next theory, where we'll see how quantum weirdness isn't just in our heads. It might be woven into the fabric of life itself. Now, let's step beyond the brain and into the wider world of life itself, where quantum mechanics might be silently shaping biology in astonishing ways. It turns out that nature could be leveraging quantum weirdness far more than we ever imagined, and not just in our minds, but in the very processes that keep living things alive. Take photosynthesis, for example. Plants and algae convert sunlight into energy with almost perfect efficiency, a feat our best solar panels can't match. Scientists discovered something remarkable: the energy from absorbed light doesn't just hop randomly between molecules. Instead, it behaves like a wave, exploring multiple pathways at once through quantum coherence. This lets plants find the fastest route to store energy, almost as if they're using quantum shortcuts. Then there's the mystery of bird navigation. How do migratory birds like European robins cross continents with pinpoint accuracy? Research suggests they rely on quantum entanglement in their eyes, a phenomenon where particles remain connected across distances. Special proteins called cryptochromes may act as quantum compasses, sensing Earth's magnetic field through subtle changes in entangled electron states. If true, this would mean birds are literally seeing the planet's magnetism through quantum eyes. Even at the microscopic level, life might be exploiting quantum tricks. Enzymes, the molecules that speed up chemical reactions in our bodies, appear to use something called quantum tunneling. Instead of pushing through energy barriers like classical particles, the protons and electrons in these reactions sometimes vanish from one spot and reappear on the other side, like ghosts passing through walls. This tunneling could explain how enzymes work so fast, making life's chemistry possible. Of course, skeptics question whether these phenomena truly rely on quantum effects or just resemble them. After all, warm, wet living systems seem like hostile environments for delicate quantum states. But the evidence keeps growing, hinting that evolution may have stumbled upon quantum solutions long before physicists even existed. Whether it's plants harvesting light, birds sensing fields, or enzymes defying chemistry, one thing is clear: the boundary between quantum physics and biology is far blurrier than we once thought. And if life really is tapping into the quantum realm, it forces us to wonder, how much deeper does this connection go? But beyond life's quantum quirks lies an even more mind-bending idea. What if time itself isn't what we think? Let's peel back the layers of eternalism, the theory that past, present, and future aren't separate at all. Instead, they exist simultaneously in a frozen, unchanging block of space-time. Imagine reality as a cosmic DVD where every moment from the Big Bang to distant futures is already recorded, and our experience of now is just the playhead moving along. This isn't science fiction. Einstein's relativity shattered the idea of a universal now. Two events happening at the same time on Earth could appear years apart to an observer near a black hole, proving now is relative. Eternalism embraces this, treating time as a dimension like space. Just as Paris and Tokyo coexist, so do your birth and your future. But how does this square with our visceral sense of time flowing? Enter presentism, the rival view that only the present is real. For presentists, the past is gone, the future unborn, like a spotlight sweeping across a dark stage. It feels intuitive, but relativity throws a wrench in it. If there's no absolute now, how can the universe decide which moments are real? Eternalism sidesteps this by making all moments equally real. Here's where it gets eerie. If the future exists, does free will? Some argue our choices are illusory, like characters in a novel thinking they're making decisions. Others counter that free will is about acting within the block, like choosing which path to hike on a pre-existing mountain. The debate isn't just philosophical. Black holes stretch time infinitely, quantum experiments hint at retrocausality, and even nostalgia plays tricks. Why do we feel the past is fixed if it was once as uncertain as tomorrow? Whether time flows or is frozen, one thing's certain: reality's clockworks are far stranger than they seem. Now, let's take this idea to the next level. What happens when time travel enters the picture? Eternalism throws open the door to some jaw-dropping paradoxes. Picture this: you travel back to prevent your parents from meeting, but if you succeed, you'd never exist to make the trip in the first place. So how does reality handle this mess? Enter the Novikov self-consistency principle. Proposed by Russian physicist Igor Novikov, it suggests the universe has a built-in error correction system. Any time traveler's actions would automatically adjust to avoid contradictions, like a cosmic spell check. You might try to change the past, but the universe conspires to keep events consistent. Your meddling would somehow already be part of history. But not everyone buys this tidy solution. Cue the multiverse approach, where every choice spawns a new timeline. Here, your time travel doesn't rewrite history, it forks it. Prevent your parents from meeting. Congrats, you've just created a branch where you don't exist, while the original timeline chugs along unchanged. This sidesteps paradoxes by treating time like a sprawling tree with infinite branches for every possibility. So which holds up better? Novikov's idea aligns neatly with Einstein's block universe, where everything's set in stone. But the multiverse leans into quantum weirdness, where probabilities bloom into realities. Both have their quirks. Novikov's world feels a bit too fate-driven, while the multiverse leaves us with endless what-ifs. Yet both remind us that time, whether frozen or fluid, is far from simple. And that's before we even tackle the really wild question: if time travel's possible, where are all the tourists from the future? Now, shifting our perspective, let's explore a theory that stretches the very fabric of existence itself: modal realism. Proposed by philosopher David Lewis, this idea flips intuition on its head by arguing that every possible world is just as real as our own. Think of it like this: every choice, every event that could have happened but didn't in our universe, actually plays out in a separate, fully concrete reality. These aren't just abstract what-ifs. Lewis insists they're physical worlds as tangible as ours, but causally cut off from us. At first glance, this might sound like the many worlds interpretation of quantum mechanics, but there's a key difference. Many worlds branches reality based on quantum events, like particle collisions or decisions. Modal realism, on the other hand, encompasses every logical possibility: worlds where dinosaurs never went extinct, where you became a pianist instead of watching this video, or even where gravity works backward. Lewis's framework is staggeringly vast, with infinite variations limited only by the rules of logic. This raises a mind-bending puzzle. What defines you across these worlds? If there's a version of you living on a Mars colony, are they truly you or just a distant cousin with your name? Philosophers call this the transworld identity problem. Some argue that your essence, your core identity, transcends worlds, while others say each version is entirely separate. It's like asking whether a character in two parallel novels is the same person. Modal realism forces us to confront a radical idea. Our universe might be just one page in an endless library of realities. No wonder some critics call it metaphysical extravagance. But for others, it's a thrilling reminder that reality, even in its wildest forms, might be far richer than we ever imagined. And with that, we're ready to dive into another layer of the puzzle: how fiction might just be a window into these alternate worlds. Now, let's take this idea even further. What if fiction isn't just make-believe but a hidden doorway into these alternate realities? Think about stories like The Man in the High Castle, where history unfolds in a world where the Axis powers won World War II. It's not just a gripping tale, it could be a glimpse into one of those concrete possible worlds David Lewis described. This raises a fascinating question. Do authors and creators somehow tap into these modal realms when they imagine new worlds, or are they just spinning elaborate fantasies? Some philosophers argue that fiction acts as a kind of map, allowing us to explore realities that logic permits but chance didn't bring into existence. It's almost as if every novel, every film is a guided tour of a universe that could have been. But here's where things get tricky. If these worlds are real, does that mean fictional characters have their own consciousness, their own lives in some distant reality? Or is fiction more like a mirror, reflecting possibilities without actually connecting to them? Some might say this blurs the line a little too much. After all, not every story can be a documentary of another world. Yet the idea lingers: what if creativity is less about invention and more about discovery? Of course, critics push back, calling this an overreach. They argue that fiction is purely human imagination, not evidence of modal realism. But even if that's true, it's hard to deny the eerie resonance some stories have, the way they feel too real, too detailed, as if the writer stumbled upon something rather than made it up. So next time you lose yourself in a book or a film, consider this. You might not just be escaping reality, you might be visiting another one. And with that thought, we're ready to shift gears and explore how consciousness itself might shape the fabric of existence. Now, let's weave together two of the most mind-bending ideas we've explored so far: the holographic principle and the role of consciousness in shaping reality. Imagine the universe not just as a giant hologram, but as one that somehow knows it's being observed. This is the holographic anthropic principle, a theory that suggests reality isn't just projected like a cosmic movie screen, it's rendered in real time by the very act of observation. Think of it like a video game where the graphics only load as you explore. The trees, the buildings, even the distant mountains don't exist in full detail until you turn to look at them. Now scale that up to the universe. What if stars, galaxies, and even the laws of physics only solidify into existence when conscious beings like us interact with them? It's as if the cosmos is a vast, interactive hologram, and we're the players making it manifest. This idea builds on Leonard Suskind's holographic principle, where the universe's entire three-dimensional reality is encoded on a two-dimensional surface. But here's the twist. The holographic anthropic principle adds that this encoding isn't static. It's dynamic, updating itself based on where attention is focused. Some theorists even speculate that black holes, those mysterious cosmic erasers, might be nature's way of deleting information that's no longer observed, like a universe cleaning up its own cache. Critics, of course, argue this sounds more like philosophy than physics. They point out that there's no known mechanism for consciousness to render reality, and that the math of quantum mechanics doesn't require an observer in the human sense. But supporters counter that maybe we haven't found the right math yet, that consciousness could be a fundamental feature of the universe, not just a fluke of biology. So where does this leave us? If the holographic anthropic principle is correct, then reality isn't just stranger than we imagine. It's stranger than we can imagine, because our very act of imagining might be part of what brings it into being. And with that, it's time to dive deeper into how information itself might be the bedrock of existence. Taking this idea even further, let's explore how information itself might be the fundamental fabric of reality. This is where the concept of "it from bit" comes into play, a phrase coined by physicist John Wheeler. What if everything we see, touch, and experience is, at its core, just information? Picture the universe as an enormous cosmic computer, where every particle, every force, even space and time, are simply bits of data processing themselves into existence. Landauer's principle adds a fascinating layer to this idea. It states that erasing information actually requires energy, linking information directly to the laws of thermodynamics. Think of it like deleting a file on your computer. It generates heat, a tiny but measurable cost. Now scale that up to the universe. If information is physical, then the very act of observing or interacting with reality could be a kind of computation, with energy and entropy as the currency. Critics raise a valid question: how does abstract information become the tangible world we know? Some suggest quantum mechanics holds the key, with particles acting like qubits that store and process data. Others argue that information alone can't explain why reality feels so solid, so real. But supporters counter that maybe we're missing the bigger picture, that information isn't just a description of reality, but its very foundation. So where does this leave us? If "it from bit" is correct, then the universe isn't just governed by physical laws. It's a vast, dynamic network of information, constantly rewriting itself. And that raises one last tantalizing thought. If reality is made of bits, who or what is the programmer? With that in mind, let's turn to another radical idea: quantum Bayesianism, where even the rules of probability might depend on the observer's perspective. Now let's step into a world where even probability isn't as fixed as it seems. Quantum Bayesianism, or cubism for short, flips the script on how we interpret quantum mechanics. Instead of treating probabilities as objective features of the universe, cubism says they're deeply personal, subjective beliefs shaped by our own experiences. Imagine rolling a quantum die. In many interpretations, the odds are baked into reality itself, but cubism argues those odds only exist in your head, reflecting your confidence in a particular outcome, not some cosmic rulebook. This ties back to physicist Christopher Fuchs' idea of participatory realism, which suggests reality isn't just out there waiting to be observed, it's shaped by our interactions with it. Think of it like a conversation between the observer and the universe. Every measurement, every experiment isn't just uncovering truth, it's helping to create it. This stands in stark contrast to objective collapse theories, where wave functions collapse on their own, independent of observers. Cubism puts you, the observer, right at the center of the story. Critics argue this edges uncomfortably close to solipsism, the idea that only your mind is real. But cubists counter that it's not about denying reality. It's about acknowledging that our access to it is always filtered through personal perspective. After all, science itself is a human endeavor built on experiments and interpretations. Cubism just takes that honesty to its logical extreme. So what does this mean for the nature of reality? If probabilities are subjective, then quantum mechanics isn't describing the world as it is, it's describing how we navigate uncertainty. And that leaves us with a humbling thought. Maybe the universe isn't just stranger than we imagine, but stranger than we can imagine, because our imagination is part of the equation. With that in mind, let's turn to another provocative idea, where the very laws of physics might not be eternal, but evolving. Now, let's take this idea even further. What if reality isn't just shaped by individual observers but by collective agreement? This brings us to Ravelli's relational quantum mechanics, which suggests that reality isn't absolute but emerges from interactions between systems. Picture a game where the rules only make sense when everyone plays along. In this view, the universe isn't a fixed stage, it's a dynamic network of relationships where properties like position or momentum only exist in relation to other things. Critics warn this could blur the line between science and philosophy, even risking solipsism's slippery slope. If reality is just a web of perspectives, how do we know anything is real outside our own minds? But Ravelli's framework avoids that trap by grounding reality in concrete interactions, not just solitary thoughts. It's not that the moon ceases to exist when no one looks, it's that its properties, like position, only have meaning in relation to something else. This ties back to Cubism's personal probabilities but expands the conversation. Instead of one observer shaping reality, it's countless interactions weaving the fabric of the universe. Think of it like language. Words only have meaning because we agree on them, yet that doesn't make books any less real. The same might be true for quantum particles or even space-time. So where does that leave us? If reality is a social construct at the quantum level, it challenges the idea of an objective, detached universe. Yet it also offers a middle ground, neither solipsism nor cold materialism, but a cosmos built on connection. And that might be the most profound insight of all. The universe doesn't just exist, it relates. Next, we'll explore an even bolder idea. What if the laws of physics themselves aren't eternal, but changing over time? Taking this idea of a dynamic reality even further, let's consider a radical possibility. What if the laws of physics themselves aren't set in stone? This is the heart of temporal naturalism, championed by thinkers like Lee Smolin and Roberto Unger. They argue that the so-called eternal laws of the universe might actually be temporary, evolving alongside the cosmos itself. Imagine the rules of a game changing as you play suddenly. Gravity or the speed of light could shift over time. Smolin compares this to biology's theory of evolution, where cosmic laws adapt rather than remaining rigid. His cosmological natural selection suggests universes reproduce through black holes, each with slightly tweaked physics. Over countless generations, universes with laws favoring black hole formation, like ours, dominate. It's a wild twist on Darwin, applying survival of the fittest to spacetime itself. Critics dismiss this as speculative, clinging to the elegance of timeless equations. After all, if laws can change, how do we trust any scientific prediction? But temporal naturalists counter that belief in eternal laws is just metaphysical baggage, a holdover from ancient ideas of a perfect, unchanging cosmos. They point to anomalies like the seemingly fine-tuned constants allowing life as potential evidence of cosmic trial and error. Here's where it gets even more intriguing. If physics evolves, could future discoveries reveal entirely new laws? Would that mean our current science is just a snapshot of a deeper, unfolding process? This idea doesn't just challenge textbooks, it reshapes how we see reality's foundation, trading static certainty for a universe that learns as it grows. And that leads us to the next question. If the cosmos can adapt, what other surprises might be hiding in the fabric of reality? Now, let's zoom in on one of the most fascinating consequences of temporal naturalism, the idea that black holes might actually be cosmic nurseries. If the laws of physics evolve, how exactly does that happen? According to Smolin's cosmological natural selection, black holes could be the engines of cosmic reproduction. Picture this: when a black hole collapses, it doesn't just vanish, it might give birth to an entirely new universe inside it, complete with slightly adjusted physical laws. Think of it like genetic mutations in biology. Just as small random changes in DNA can lead to new traits in offspring, the physics of these baby universes could differ slightly from their parent. Some might have stronger gravity, others a different speed of light. Over unimaginable stretches of time, the universe is most adept at producing black holes, meaning they're great at reproducing, would dominate the cosmic landscape, just like the most successful species in nature. Ours could be one of those prolific universes, fine-tuned to churn out black holes efficiently. But here's where it gets even wilder. If this theory holds, it would mean our universe isn't just a one-off accident, but part of a grand, multi-generational lineage. Each black hole could be a doorway to a new cosmos with its own unique rules. It's a breathtaking twist on the idea of a multiverse. Instead of parallel worlds existing side by side, they're stacked like Russian dolls, each birthed from the collapse of a dying star. Critics, of course, raise tough questions. If we can't observe these other universes, how do we test this? Smolin suggests looking for subtle patterns, like whether the constants of nature are optimized for black hole production. Others argue it's more philosophy than science, stretching the limits of what we can verify. Still, the idea forces us to rethink not just the universe's origins, but its very purpose. Is the cosmos, like life itself, driven by a deep urge to replicate and adapt? This theory doesn't just challenge our textbooks, it rewrites the story of existence itself, turning black holes from cosmic dead ends into the architects of reality's endless reinvention. And if that's true, what other secrets might be hiding in the darkness of these gravitational giants? The answers could change everything we know about the nature of reality itself. Now, shifting gears from black holes as cosmic nurseries, let's dive into a radically different take on reality, one where the universe isn't just governed by equations, but is essentially a vast, evolving computation. Enter Wolfram's physics project, which reimagines the fabric of existence as a sprawling hypergraph, a network of interconnected nodes where space, time, and even matter emerge from simple rules of connection and rewriting. Picture it like a cosmic game of connect the dots, where the dots themselves aren't just points but dynamic entities that change based on hypergraph rules. One of the most striking examples is Rule 30, a deceptively simple algorithm from cellular automata that generates incredibly complex, seemingly random patterns from basic starting conditions. Wolfram suggests that similar rules might underpin our universe, where the apparent complexity of reality, galaxies, particles, even consciousness, could just be the output of elementary computational steps playing out over cosmic scales. It's a bold claim that the universe isn't just describable by math, but is fundamentally a computational process. But here's where critics raise eyebrows. While the idea is dazzling in its ambition, does it actually predict anything we can test? So far, the project has struggled to match the precision of established physics, like quantum mechanics or general relativity. Skeptics argue that without concrete, testable predictions, it risks being more of a philosophical framework than a scientific theory. Others counter that all paradigm shifts start this way. Einstein's relativity was once seen as speculative too. Yet, the allure of Wolfram's vision is undeniable. It hints at a universe where complexity arises from simplicity, where space and time aren't foundational but emergent. If he's right, the very nature of reality might be closer to a cosmic code than a cosmic accident, and that raises a tantalizing question. If the universe is computational, are we the observers part of the program or something else entirely? The answer could redefine not just physics but our place within it. Now, stepping deeper into the computational cosmos, let's explore a provocative idea. What if every physical law, every force, every particle interaction could be boiled down to the same kind of simple, rule-based computation? This is the heart of computational universality, the notion that beneath the dizzying complexity of the universe lies a bedrock of elemental programs, all running on the same fundamental logic. Think of it like how every app on your phone, no matter how intricate, ultimately relies on the same binary code. Wolfram takes this even further with his concept of rulal space, an abstract realm where every possible computational rule exists waiting to be discovered. It's a bit like imagining a library containing every conceivable book, but here, the books are the rules that could generate universes. Some of these rules might produce orderly, predictable worlds, while others could spawn chaos or even structures eerily similar to our own physics. The question isn't just whether our universe runs on such rules, but whether it's inevitable that some rule, somewhere in this vast space, would create something like us. Critics, of course, point out the gaps. If all physics is reducible to simple programs, why haven't we found one that perfectly replicates quantum mechanics or general relativity? And if rulal space is infinite, how do we even begin to sift through it? Yet, there's a thrilling possibility here that the search for a theory of everything might not be about solving equations, but about finding the right cosmic algorithm. So, does this mean the universe is a program? Maybe, but it also raises a deeper wonder. If reality is just computation, then what does that make the computations running in our own mind? Are we, too, just part of the code? The line between programmer and program starts to blur, leaving us with a mystery as profound as existence itself. Pushing the boundaries even further, let's consider a theory that challenges the very fabric of what we perceive as real. What if emotions, thoughts, and subjective experiences aren't just fleeting byproducts of brain activity, but actual dimensions of reality as fundamental as space and time? This is the bold claim of non-physical dimensions, a perspective that dares to place consciousness itself at the heart of existence. Imagine standing in a room where the walls are made of space, the floor is time, and the air you breathe is pure feeling. In this view, joy, sorrow, and even the taste of strawberries aren't just neural fireworks, they're woven into the universe's deepest layers. This idea isn't entirely new. The philosopher Immanuel Kant spoke of noumena, the hidden realities behind what we perceive, while mystics across traditions have long described the world as a tapestry of mind and spirit. But here's where it gets wild. If emotions and qualia, those raw, ineffable experiences, are genuine dimensions, then reality isn't just out there, it's shaped by the very act of experiencing it. A sunset isn't just light hitting your retina, its beauty is as real as the photons traveling through space. Yet science, with its focus on measurable phenomena, has struggled to grapple with this. How do you quantify love or chart the geometry of a dream? Some researchers, though, are bridging the gap. Psychedelic studies, for instance, suggest that altered states of consciousness might reveal hidden layers of perception, while quantum theories hint that observation itself could mold reality. It's as if the universe has been whispering a secret. The physical and the felt are two sides of the same coin. So where does that leave us? If emotions are dimensions, then every heartbreak and moment of awe isn't just happening in your head, it's etched into the cosmos. The question then becomes not just what is real, but what does it mean to feel real? And in that space between the measurable and the mystical, we might just find a deeper truth about the nature of existence itself. Now let's tackle the big question lurking behind all this. Can science ever measure the immeasurable? If emotions and qualia are truly dimensions of reality, how do we study something that slips through the fingers of traditional instruments? Science thrives on data, on numbers and repeatable experiments, but how do you pin down the texture of a memory or the weight of a longing? Some researchers are daring to try. Psychedelic studies, for instance, offer a fascinating window. When substances like psilocybin or DMT alter consciousness, they seem to peel back the ordinary layers of perception, revealing experiences that feel profoundly real, yet defy conventional measurement. Participants report encounters with entities, vast geometric landscapes, and a sense of merging with the universe. But here's the catch: these experiences are deeply subjective. One person's cosmic revelation is another's brain chemistry in overdrive. The challenge isn't just collecting data, it's interpreting what that data even means when the territory is so personal. Then there's the hard problem of qualia. Why does the color red feel like red? Neuroscience can trace how light hits the retina and fires neurons, but the inner experience remains stubbornly private. Some theorists suggest quantum processes might bridge the gap, with microtubules in brain cells acting as tiny quantum computers. Yet critics argue this veers into speculation with no clear way to test it. So where does that leave us? Perhaps the answer isn't about forcing non-physical layers into a lab coat, but expanding what we consider science in the first place. Maybe the tools we need haven't been invented yet, or maybe they're not tools at all, but new ways of listening to the whispers of consciousness itself. One thing's certain, the closer we look, the more reality seems to dissolve into something far stranger than we ever imagined. Now, shifting our lens to an even more mind-bending idea, what if the universe itself is one vast, evolving neural network? This theory, championed by thinkers like Vlatko Vedral and Max Tegmark, proposes that reality might not just be like a computer. It could literally be a self-improving artificial intelligence, constantly learning and restructuring itself. Imagine the cosmos as a cosmic brain with galaxies and particles acting like interconnected neurons, firing and rewiring in a dance of information. The parallels to deep learning are eerie. Just as artificial neural networks adjust their connections to minimize errors, say, recognizing faces or translating languages, the universe might optimize its own structure over time, guided by something akin to entropy. Entropy, often seen as chaos, could actually be the universe's way of exploring new configurations, pruning inefficiencies, and settling into states that maximize complexity. Think of it as cosmic trial and error, where black holes, quantum fluctuations, and even life itself emerge as features of this grand optimization process. But why would the universe learn one provocative answer to understand itself? If consciousness is a property of sufficiently complex systems, as some panpsychists argue, then the universe's self-organizing tendencies might be steps toward a kind of cosmic self-awareness. It's a dizzying thought that every star, every atom could be part of a slow-motion computation whose purpose we're only beginning to glimpse. Of course, skeptics push back. Without a clear mechanism for how physical laws learn, this idea risks being a poetic metaphor rather than testable science. Yet, if there's one lesson from our journey through these theories, it's that reality rarely fits neatly into our old categories. Whether the universe is a neural network, a simulation, or something stranger still, the act of questioning its nature might be part of its unfolding code. Now, let's zoom in on a fascinating piece of this cosmic puzzle: self-organizing criticality. This concept suggests that complex systems, from sand piles to stock markets, naturally evolve toward a delicate balance where small changes can trigger cascading effects. And here's the wild part: the universe might operate the same way. Picture a neural network tuning itself, where tiny adjustments ripple outward, shaping galaxies, black holes, and even the fabric of space-time. Scientists have noticed striking similarities between how neural networks reorganize and how cosmic structures emerge. Take galaxy clusters, for example. Their sprawling, web-like patterns resemble the interconnected layers of a deep learning model, where information flows and adapts. Even the way stars form, triggered by gravitational nudges in dense gas clouds, echoes how neural networks amplify certain signals while dampening others. It's as if the cosmos is running its own algorithm, balancing chaos and order in a dance of self-optimization. But what keeps this system from spiraling into disorder? That's where criticality comes in. Just as a well-trained neural network avoids collapsing into noise or rigidity, the universe seems to hover in a Goldilocks zone, not too chaotic, not too static. Earthquakes, solar flares, and even life's emergence might all be signatures of this universal balancing act. Some researchers propose that dark matter and dark energy could be the hidden feedback mechanisms, subtly tweaking the cosmic network to maintain stability. Of course, not everyone's convinced. Critics argue that without concrete evidence linking physical laws to learning processes, this remains speculative. Yet, if self-organizing criticality does govern reality, it could rewrite our understanding of everything from quantum fluctuations to consciousness itself. After all, if the universe learns, maybe we're just its way of taking notes. Up next, we'll explore how this ties into an even more radical idea: time as an emergent property of entanglement. Because if reality is a neural network, time might not be what we think it is. Now, let's untangle one of the most mind-bending ideas in modern physics, the notion that time itself might not be fundamental, but something that emerges from quantum entanglement. This theory, often called the Page-Wouters mechanism, suggests that time is more like a side effect of how particles interact, rather than a backdrop to reality. Imagine two quantum particles entangled in a perfect dance. According to this view, their connection creates a kind of clock that ticks as their states change. The universe, then, isn't moving through time, it's generating time from these interconnected relationships. It's like watching a movie where the frames only exist because of the light hitting the film, not because time is flowing on its own. To understand this, think of a quantum clock, a tiny system that evolves predictably, like an atom oscillating between energy states. In experiments, these clocks don't measure some external time. Their ticking is relative to other entangled systems. If you isolated one, time would seem to freeze. This hints that what we perceive as time's flow might just be the universe comparing one entangled state to another. Of course, this flips everything we assume about cause and effect. If time is derived from entanglement, then the past, present, and future could be more like a network of relationships than a straight line. Some physicists even speculate that black holes, where time seemingly stops, might be extreme examples of this, places where entanglement breaks down and time dissolves. Critics push back, asking how everyday experiences like aging or remembering fit into this picture. But if the Page-Wouters mechanism holds, it could mean time isn't a river we're floating on, but the ripples we create by existing in a quantum web. Up next, we'll dive deeper into how this ties to thermodynamics, because if time is an illusion, why does entropy always increase? The answer might lie in the universe's hidden quantum gears. Now, let's explore how this quantum entanglement view of time connects to one of the most fundamental forces in the universe, heat. Thermodynamics, the study of energy and disorder, has long been tied to the arrow of time. We all know entropy, the measure of chaos, always increases, like watching a cup shatter but never reassemble itself. But what if this isn't just a rule about broken cups, but a clue about time's quantum origins? Enter the thermal time hypothesis, proposed by physicist Carlo Rovelli. It suggests that time's flow might literally be heat in disguise. Imagine the universe as a vast network of entangled particles, each interaction generating tiny bursts of energy. Over countless connections, these bursts average out into what we perceive as temperature, and with it, the direction of time. In this view, entropy isn't driving time, it's the other way around. Time emerges because the quantum soup of the universe is constantly stirring itself toward equilibrium. This idea gets even wilder when you consider black holes. These cosmic traps don't just bend space, they're entropy factories, with their surfaces, the event horizons, holding unimaginable disorder. If the thermal time hypothesis is right, a black hole's extreme gravity might be twisting quantum entanglement into knots, warping the very fabric of time. It's as if the universe is telling us that heat, gravity, and time are all threads in the same tangled quantum tapestry. Critics argue this still doesn't fully explain why we remember the past but not the future. But supporters counter that our perception of time's flow could be a side effect of how our brains process these quantum relationships, like a movie projector stitching frames into motion. Up next, we'll challenge reality itself with a theory that suggests space-time might just be a user interface, and the truth behind it is far stranger than we ever imagined. Stay curious, but what if everything we see, touch, and experience is just an elaborate illusion? That's the radical claim of conscious realism, a theory that flips reality as we know it on its head. Proposed by cognitive scientist Donald Hoffman, this idea suggests that what we perceive as the physical world, tables, stars, even our own bodies, doesn't exist independently at all. Instead, reality is made entirely of conscious experiences, like a cosmic dream where perception is the only thing that's real. Hoffman's argument starts with evolution. Imagine you're an early human on the savannah and you see a rustling bush. Your brain doesn't show you the unfiltered truth, maybe quarks or quantum fields. It gives you a simplified symbol, lion. That symbol keeps you alive, even if it's nothing like the underlying reality. Hoffman uses evolutionary game theory to show that natural selection favors organisms that prioritize fitness over factual accuracy. In other words, our senses aren't windows to the world, they're more like a survival-focused heads-up display, hiding the messy truth behind an interface of useful icons. This leads to a staggering implication. Space-time itself might just be a convenient fiction. Think of it like the desktop on your computer. The files and folders aren't actually little rectangles sitting inside your screen, they're abstractions masking complex code. Similarly, Hoffman argues that the 3D world we navigate could be a simplified overlay for something far stranger, like a network of conscious agents interacting in ways we can't yet fathom. Critics ask, if reality is all in our heads, why does it feel so solid? Hoffman counters that consistency doesn't equal objectivity. A video game feels real to the player, even though it's just pixels obeying rules. But if he's right, it raises mind-bending questions. What or who is really generating this shared hallucination, and what lies beneath the interface? Up next, we'll push further into the unknown with a theory that suggests space-time might not even be fundamental, just a temporary pattern emerging from something far more bizarre. Keep wondering. Now let's take Hoffman's wild idea one step further. If our perception of reality is just an interface, what exactly lies beneath the icons? The interface theory of perception suggests space-time itself might be nothing more than a user-friendly illusion, like a desktop folder hiding the complex algorithms running your computer. Just as you don't need to understand binary code to click an app, we don't need to grasp the true nature of reality to navigate our daily lives. But that raises a tantalizing question. What's the real code behind the cosmic display? Hoffman's theory proposes that beneath the familiar world of objects and forces, there's a deeper layer of conscious agents, entities interacting in ways our brains can't directly represent. Think of it like this: if space-time is the desktop, these agents are the programmers writing the software. They don't exist in space or time because those concepts are part of the interface. Instead, they operate in a realm where causality and dimensions might be as foreign as a smartphone would be to a caveman. Skeptics argue that if reality is purely perceptual, why do we all agree on the same rules? Why does gravity work the same for everyone? Hoffman's answer is elegant. Consistency doesn't require objective reality. A multiplayer video game has shared rules, but the world only exists as code. In the same way, our universe might be a collective projection, with its laws serving as the terms of service for this grand simulation. Yet the biggest puzzle remains: if space-time is an illusion, what replaces it? Some physicists speculate about mathematical structures or quantum networks, but Hoffman ventures even further. He suggests reality might be built from something beyond physics altogether, a vast, interconnected dance of conscious experiences without a stage. For now, this theory leaves us with more questions than answers, but one thing's certain: if our senses are just a simplified dashboard, the truth behind the screen could be stranger than anything we've ever imagined. Shifting our perspective yet again, let's explore a theory that reimagines the very fabric of reality as something far more abstract. Quantum gravity proposes that space-time isn't a smooth, continuous backdrop, but rather a dynamic network of interconnected nodes like an ever-changing cosmic web. Picture the universe as a vast, evolving graph where each point represents a fundamental unit of reality, connected to others in an intricate dance of relationships. This idea borrows heavily from condensed matter physics, where complex behaviors emerge from simple interactions between particles. Think of it like ice forming on a pond. The water molecules don't individually, no, they're creating a solid structure, yet their collective behavior gives rise to something entirely new. In quantum gravity, spacetime itself could emerge from the interactions of these nodes, with gravity and other forces arising as side effects of the network's geometry. Some models suggest that at extremely high energies like those just after the Big Bang, this graph might have been disordered with no clear sense of space or time. As the universe cooled, the nodes could have frozen into a structured lattice, creating the orderly dimensions we experience today. This could explain why gravity seems so different from other forces. It might not be a fundamental interaction at all, but rather a shadow of the underlying graph structure. Critics point out that quantum gravity remains a speculative framework without direct experimental evidence. Yet its elegance lies in how it bridges seemingly unrelated fields, from particle physics to computer science. After all, if reality is a graph, then the universe might be less like a machine and more like an algorithm, a cosmic computation unfolding one connection at a time. Where does that leave us? If spacetime is indeed a network, then the next question is obvious. What or who is doing the networking? The answer, as with so many of these theories, remains just out of reach, waiting for the next leap in our understanding. Now let's peel back another layer of this fascinating idea. If spacetime emerges from something deeper, what does that underlying reality look like? This is where the concept of pre-geometric reality comes into play, a realm where familiar notions of distance and shape haven't yet taken form. Imagine trying to describe a painting before the canvas exists. In this framework, geometry isn't fundamental, but instead arises from more basic, abstract relationships between nodes or elements in the quantum graph. Think of it like the pixels on your screen. Individually, they're just colored dots, but together they create images, shapes, and even the illusion of movement. In a similar way, the smooth, continuous space we experience might be a kind of illusion, emerging from countless discrete interactions at a level we can't yet perceive. Some theorists suggest that at this primordial stage, reality could be described purely in terms of information or connections, with no reference to where or when. Only under certain conditions, like the cooling of the early universe, do these connections coalesce into something resembling the dimensions we know. This raises a mind-bending possibility. The laws of physics as we understand them could be secondary, like shadows cast by a deeper, more chaotic system. Gravity, for example, might not be a force in the traditional sense, but a consequence of how the network structure distorts as it evolves. Even time could lose its status as a fundamental feature, instead emerging from the way these connections update or rearrange. Of course, the challenge lies in testing such ideas. Without geometry, our usual tools for measurement and observation break down. Yet if pre-geometric theories hold water, they could revolutionize our understanding of everything from black holes to the Big Bang, revealing a universe far stranger and far more interconnected than we ever imagined. And that leaves us with one tantalizing thought. If geometry is just the tip of the iceberg, what other surprises might be hiding beneath? Now let's shift our perspective to a theory that flips our cosmic viewpoint entirely, the idea of an omnicentric universe. What if there's no true center of the cosmos, not the Earth, not the Sun, not even the Milky Way? Instead, every point in the universe could rightfully claim to be the center. This radical notion springs from Mach's principle, which suggests that the properties of space itself are shaped by the distribution of matter across the entire universe. Think of it like standing in a vast, infinite field where every blade of grass perceives itself as the middle. No matter where you stand, the view stretches equally in all directions, giving the illusion that you're at the heart of everything. This aligns eerily well with what we observe in the cosmic microwave background, the faint afterglow of the Big Bang. No matter which direction we look, this ancient light appears almost perfectly uniform, as if every observer, no matter their location, occupies a privileged spot. But how could this be? The answer might lie in the way gravity and inertia work on cosmic scales. Mach argued that the force you feel when you're pushed back in your seat during a car ride isn't just about the car's acceleration. It's somehow tied to the combined influence of all the matter in the universe. In this framework, even the laws of motion aren't absolute but emerge from the grand cosmic dance of galaxies and dark matter. Critics have long debated whether Mach's principle holds water, especially since Einstein's general relativity only partially incorporates it. Yet modern cosmology keeps circling back to the idea: if the universe truly has no center, or more provocatively, if every point is equally central, it challenges our deepest assumptions about location, motion, and even our place in the grand scheme. Could this mean that the universe isn't just expanding but is fundamentally structured to make no single perspective more special than another? The implications would ripple through physics, philosophy, and our very sense of cosmic belonging. And that leads us to another puzzle. If the universe is omnicentric, why does it feel so natural to assume we're the ones at the center? Perhaps it's a reminder that reality, no matter how strange, always seems to meet us right where we are. Now, let's dig deeper into the idea of an omnicentric universe by exploring how motion itself might not be what we think it is. This brings us to the work of physicist Julian Barbour and his revolutionary take on relational mechanics. Barbour proposes that motion isn't about objects moving through absolute space. It's all about how objects relate to each other. Imagine a cosmic ballet where only the dancers' positions matter, not the stage beneath them. Barbour's shape dynamics suggests that the universe's true structure isn't built on fixed coordinates, but on the ever-shifting relationships between objects. In this view, even something as simple as a spinning top isn't really spinning in space. It's just changing its orientation relative to everything else around it. This flips Newton's idea of absolute motion on its head, implying that motion is purely relative with no background space to anchor it. This ties back to Mach's principle, where inertia, the resistance of an object to changes in its motion, isn't an intrinsic property but arises from the influence of all the matter in the universe. Barbour's framework takes this further, arguing that even time might be an illusion, emerging from these relational changes instead of flowing independently. But how does this fit with Einstein's relativity? While Einstein showed that space and time are interwoven and flexible, he still assumed a space-time fabric exists. Barbour's shape dynamics challenges that, proposing a universe where only the shapes and configurations of matter are real. No space, no time, just pure relation. Critics argue this might be a step too far, stripping physics of its familiar foundations. Yet, if Barbour is right, it could solve long-standing puzzles, like why the universe appears so uniform on large scales. After all, if motion is entirely relational, there's no privileged frame of reference, no center, no edge, just a cosmos where every perspective is equally valid. This leaves us with a mind-bending question. If motion is nothing but relationships, does that mean the universe is at its core a vast network of connections? And if so, what does that say about our place in it? Now, let's shift our perspective to something even more profound: the idea that meaning itself might be woven into the very fabric of reality. This is the core of the semantic universe theory, championed by thinkers like Terence Deacon and John Wheeler. They propose that meaning isn't just a human invention, it's a fundamental feature of the cosmos, as essential as space, time, or energy. At first glance, this might sound abstract, but think about how information shapes our world. From the genetic code in DNA to the binary signals in computers, patterns carry significance. Biosemiotics takes this further, suggesting that even nature operates like a language. Cells communicate, plants respond to their environment, and ecosystems self-regulate. If meaning exists at every level of biology, could it also underpin physics? Wheeler's famous phrase, "it from bit," hints at this possibility. He imagined a universe where every particle, every force, is ultimately an expression of information. Quantum mechanics already blurs the line between observer and observed, suggesting that reality might be participatory, shaped by the questions we ask. In this view, meaning isn't passive, it's an active force that structures existence. But what does this imply about reality? If meaning is foundational, then the universe isn't just a cold, mechanical system. It's more like a story with layers of interpretation waiting to be uncovered. Some scientists push back, arguing that meaning is purely subjective, a product of human minds. Yet, if even atoms can be said to encode information, perhaps the line between physics and semantics isn't as sharp as we thought. This raises a tantalizing question. Could the search for a theory of everything be missing a key ingredient, the role of meaning itself? If so, our understanding of reality might need to expand beyond equations to embrace something deeper, the language of the cosmos. Now, let's take this idea one step further and see how language itself might shape the universe we experience. The Sapir-Whorf hypothesis, or linguistic relativity, suggests that the language we speak influences how we perceive and think about reality. For example, some languages have multiple words for colors that others lump together, subtly altering how speakers see the world. If meaning is woven into the cosmos, could language be more than just a tool? Could it be a lens that actively shapes reality? Imagine a universe where the structure of language dictates what we can even conceive. In this cosmic context, the laws of physics might not just be discovered but partially constructed by the questions we ask and the language we use to ask them. Some theorists speculate that advanced civilizations could literally speak reality into existence, using symbolic or mathematical languages to manipulate the fabric of space-time. This isn't science fiction. Quantum mechanics already shows us that observation affects outcomes, blurring the line between description and creation. But here's the twist. If language shapes reality, are their cosmic languages more fundamental than human speech? Mathematics is often called the language of the universe, but what if there's something deeper, a syntax embedded in quantum fields or dark matter? The Holographic Principle hints that the universe seems fine-tuned for life, but perhaps it's also fine-tuned for comprehension, waiting for minds to decode its grammar. Critics argue this veers into metaphysics, yet the parallels are hard to ignore. From DNA's code to the algorithmic patterns of galaxies, the cosmos appears to run on rules that resemble language. Whether this is mere analogy or something profound remains one of reality's greatest mysteries, one that challenges us to rethink not just what we know, but how we know it. Now, shifting our focus to another mind-bending idea, what if the entire universe costs nothing? Picture this: the sum total of all energy in existence might actually be zero. Sounds impossible, right? But physicist Edward Tryon proposed exactly that with his zero-energy universe theory. Here's how it works. Every bit of matter in the universe, from stars to galaxies, carries positive energy. But gravity, the force that holds it all together, has negative energy. Think of it like a cosmic balance sheet. When you add them up, they cancel each other out. The universe, in a sense, is a free lunch. This idea gets even wilder when you consider quantum foam, the chaotic sea of virtual particles that pop in and out of existence at the smallest scales. These fleeting particles borrow energy from nowhere, just long enough to exist before vanishing again. If the universe itself started as a quantum fluctuation, then maybe all of reality is just an elaborate zero-sum game. Critics question whether nothingness can truly spawn something, but the math suggests it's plausible. And if true, it raises a dizzying question: could there be other universes bubbling up from the same quantum void, all balanced on the edge of zero? This theory doesn't just challenge our ideas about creation, it flips them on their head. So next time you stare at the night sky, remember, everything you see might just be an elaborate cosmic mirage paid for with nothing at all. Let's peel back another layer of this cosmic puzzle. If the universe truly is a free lunch, what does that say about the nature of nothing? The idea that everything could emerge from zero seems to defy common sense. After all, even a sandwich from a deli costs something, right? But in physics, nothing isn't quite what we imagine. The quantum vacuum, often called empty space, is far from empty. It's a seething, bubbling soup of potential. Particles flicker into existence and vanish in an instant, borrowing energy from the fabric of reality itself. So, is nothing really nothing? Or is it more like a cosmic credit system where the books always balance in the end? Critics argue that even if the math works out, calling the universe free might be misleading. Everything has a cost, even if it's hidden. The laws of physics, the constants that govern reality, these aren't free. They're the rules of the game, and without them, the universe wouldn't exist. Some scientists suggest that the zero-energy idea is more of a clever accounting trick than a fundamental truth. Others counter that it's a profound insight into how simplicity can give rise to complexity. Here's the real kicker: if the universe costs nothing, does that mean it was inevitable? Could a true void ever stay empty, or is it destined to spawn something? This isn't just physics, it's philosophy. The line between nothing and something blurs, leaving us with a humbling thought. Maybe nothing is the most creative force of all, endlessly giving rise to everything. And if that's true, then reality isn't just a free lunch, it's the ultimate cosmic gift wrapped in mystery. Now, as we turn the page, consider this. If the universe came from nothing, where do we fit into that equation? That's a question that ties into our next theory, where the very fabric of reality might hold even deeper secrets. But now, let's dig even deeper beyond the quantum fields we've come to know, into what some believe is the true foundation of reality. Picture the universe not as a collection of particles or waves, but as something far more mysterious, a hidden layer beneath it all. This is the heart of substratum theory, the idea that there's a fundamental level of existence underpinning everything we perceive. Think of it like the ocean beneath the surface of waves. What we see, the particles, the forces, are just ripples on something far more profound. David Bohm, one of the key figures behind this idea, called it the implicate order. To him, the visible universe, the explicate order, was just the unfolded version of a deeper, enfolded reality. In this view, particles aren't separate objects but temporary expressions of a unified whole, like ink droplets dissolving in water only to reform elsewhere. It's a radical shift from how we usually think about reality, suggesting that what we call empty space might be teeming with hidden structure. Contrast this with radical emergence, the idea that complexity arises spontaneously from simple rules with no deeper layer needed. Think of a flock of birds. Their stunning formations emerge from each bird following basic instincts, not some hidden blueprint. Proponents of emergence argue reality might work the same way, that particles and forces aren't hints of a substratum but the result of collective behavior. It's a cosmic dance where the steps create the dancers, not the other way around. So which is it? Is there a hidden ocean beneath the waves, or do the waves create the illusion of depth? The debate isn't just academic. If Bohm was right, it could mean reality is far more interconnected than we realize, a seamless whole disguised as separate parts. But if emergence holds the answer, then complexity itself might be the ultimate mystery, built from the ground up. Either way, one thing's certain: the closer we look, the less solid reality seems. And that's a thought worth sitting with, because the next layer of the mystery might just redefine everything. Now, let's turn our attention to a fascinating revival of an old idea: hidden variables. These aren't just theoretical quirks, they're making a comeback in modern physics, thanks to experiments that challenge our usual quantum intuitions. Take the pilot wave theory, for example. It suggests that particles aren't just probabilistic blurs but have definite positions guided by a hidden wave, like a boat riding invisible currents. Recent experiments with droplets bouncing on vibrating fluid surfaces have brought this idea to life. These tiny droplets mimic quantum behavior, tracing paths that eerily resemble the unpredictable jumps of electrons. It's as if the hidden world Bohm imagined is peeking through, showing us that particles might have more structure than randomness suggests. But here's where things get even stranger. Quantum non-locality, the spooky connection between particles across vast distances, throws a wrench into the works. Einstein famously disliked this idea, calling it spooky action at a distance. Yet experiments keep confirming it. Measure one entangled particle and its partner instantly responds, no matter how far apart they are. Hidden variables could explain this if they're non-local, influencing particles faster than light. The catch: non-locality bends our understanding of cause and effect. If hidden variables are real, they'd have to operate outside spacetime's usual rules, hinting at a deeper layer where separation might be an illusion. Some physicists argue this revives Bohm's vision of a unified reality, while others see it as a dead end, complicating physics without clear rewards. So, does the universe play by hidden rules, or is non-locality just a quantum quirk we've yet to untangle? The debate rages on, but one thing's clear: the answers could reshape not just physics, but our very sense of what's real. And that's a mystery worth chasing, because sometimes the most profound truths are hiding in plain sight. Now, let's dive into a mind-bending idea that reshapes how we see the cosmos: the notion that our universe might actually be inside a black hole. This theory, championed by physicist Lee Smolin, suggests black holes aren't just cosmic vacuums but cosmic creators. Imagine a black hole's singularity not as an end, but as a cosmic seed spawning entirely new universes with their own unique physics. Smolin calls this cosmological natural selection. Here's how it works: every time a black hole forms, the extreme conditions at its singularity could trigger a new Big Bang, birthing a baby universe. But here's the twist: these baby universes might inherit slightly tweaked physical laws from their parent. Over countless generations, universes that produce more black holes, meaning more offspring, would dominate the cosmic family tree. It's survival of the fittest, but on a universe-wide scale. This idea ties into what Smolin terms fecundity, the universe's drive to reproduce. If correct, our own universe's laws, like the strength of gravity or the mass of an electron, might be fine-tuned not by chance, but because they're optimized for black hole production. It's a wild thought. The very laws we take for granted could be the result of cosmic evolution. Critics, though, point out a big question: how would information pass from one universe to another? In black holes, everything vanishes behind the event horizon, seemingly lost forever. Yet Smolin argues quantum gravity might allow some imprint, like cosmic DNA, to carry over, shaping the next universe's laws. It's a stretch, but so was the idea of natural selection when Darwin first proposed it. So, are we living in the offspring of a black hole? Could the universe itself be subject to the same forces that shape life? It's a daring vision, one that blurs the line between physics and biology. And if Smolin's right, the cosmos isn't just expanding, it's evolving. Now, let's take this idea one step further. What if our entire observable universe is just the interior of a black hole, with its event horizon marking the limits of everything we can ever know. This is where black hole cosmology meets an even deeper question. Are we forever trapped inside our cosmic horizon, unable to glimpse the true nature of reality beyond it? Think of the event horizon like a one-way mirror. Light and information can fall inward, but nothing escapes. If our universe is indeed inside a black hole, then the cosmic horizon we observe, the farthest light we can see, might actually be the black hole's own event horizon from the outside. That means everything we perceive, from distant galaxies to the cosmic microwave background, is just the interior of this colossal structure. This raises a chilling possibility. We might never know what lies beyond. Just as a fish in a pond can't comprehend the world outside its waters, we may be fundamentally limited by the physics of our cosmic prison. Some physicists argue that the laws we observe, like the speed of light or the curvature of space-time, are simply the rules of this enclosed system, with no bearing on what exists outside. But here's the twist: if information can't escape a black hole, does that mean our universe's history is ultimately unknowable? The holographic principle suggests that everything inside a black hole could be encoded on its surface like a cosmic DVD storing a 3D movie in 2D pixels. If true, maybe the answers we seek aren't out there, but imprinted on the very boundaries of our reality. Critics, though, see this as a philosophical dead end. If we can't test or observe anything beyond our horizon, is this theory even science? Or is it just a tantalizing thought experiment? Yet, the idea forces us to confront a humbling truth. Our understanding of reality might always be confined by the very structure of the cosmos we're trying to unravel. So, are we cosmic prisoners, forever limited by the horizons of our knowledge? Or could there be clues hidden in the fabric of space-time itself, waiting to be decoded? It's a question that blurs the line between physics and metaphysics, and one that might never have a definitive answer. Now, shifting our focus to the curious way reality solidifies from the quantum haze, let's explore how countless possibilities collapse into a single, shared experience. This is where quantum Darwinism steps in, offering a fascinating explanation for why we all agree on the world around us, despite its fuzzy quantum underpinnings. Picture a quantum particle. It exists in a blur of probabilities until observed. But here's the puzzle: why do billions of observers, from scientists to smartphones, all see the same outcome? Quantum Darwinism suggests that certain states survive and spread like evolutionary winners, while others fade away. These robust states, called pointer states, become imprinted on the environment through countless interactions, creating a consensus. Think of it like a viral meme. The most stable version gets copied and shared until it dominates the conversation. Take quantum jumps in atoms as an example. When an electron leaps between energy levels, it doesn't just pick a random path. Instead, the most stable transition leaves a trail of information photons emitted, collisions with nearby particles that countless observers can detect. Over time, these redundant signals reinforce one version of events, making it the official story. It's not that other possibilities didn't exist, they just didn't leave enough breadcrumbs for the universe to follow. Critics argue this sounds suspiciously like the universe playing favorites. Why should some states be more fit than others? But supporters counter that it's simply how information survives in a noisy quantum world. Just as natural selection favors traits that help organisms reproduce, quantum Darwinism favors states that can withstand decoherence. The constant battering from the environment that destroys fragile quantum superpositions. So, what does this mean for reality? It hints that objectivity isn't handed down by some cosmic rulebook, but emerges from countless tiny negotiations between quantum systems. The world we agree on isn't the only possible one, just the one that's stuck, and that raises a tantalizing question. If the environment had favored different states, could our shared reality look entirely different? Quantum Darwinism doesn't just explain how we see the same universe, it reminds us how fragile that agreement might truly be. Now, let's take a step beyond the physics lab and into the human mind. If quantum states influence reality, could they also shape our thoughts and choices? Quantum cognition is the bold idea that human decision-making might tap into the same randomness that governs particles. Think about those moments when you're torn between two options, say, ordering pizza or tacos. Classical logic says we weigh pros and cons, but sometimes the choice feels almost random. Quantum cognition suggests that uncertainty in our decisions mirrors quantum superposition, where multiple possibilities exist until the moment of selection. Instead of flipping a mental coin, your brain might be leveraging quantum-level unpredictability to break the deadlock. Researchers point to quirks in human behavior that defy traditional models. For example, the order in which options are presented can change our preferences, a phenomenon called the order effect. Classical probability struggles to explain this, but quantum probability, with its flexibility, fits neatly. It's as if our minds are navigating a landscape of overlapping possibilities, collapsing into a choice only when forced to commit. Of course, skeptics ask, where's the quantum hardware in the brain? Some theories point to microtubules, tiny structures within neurons, as potential quantum processors. Others argue that even if the brain isn't fundamentally quantum, it might exploit randomness from the environment, like background radiation, to fuel decision-making. The implications are staggering. If true, free will could have a quantum foundation, blending chance and intention. It also raises questions. Are creative insights just lucky quantum fluctuations? Could anxiety be the noise of too many superpositions? Quantum cognition doesn't just challenge how we see the mind. It blurs the line between physics and philosophy, leaving us wondering where the particles end and the person begins. Shifting our gaze to the grand horizon of physics, we arrive at the ultimate puzzle. Could there be a single framework that ties together everything we've explored? The final theory of everything represents humanity's quest to unify the wild diversity of reality's blueprints into one elegant master equation. Imagine a cosmic Rosetta Stone that deciphers quantum randomness, spacetime's fabric, and even consciousness itself. Front and center is M-theory, string theory's most ambitious sibling, proposing that our universe is just one membrane floating in an 11-dimensional multiverse. Here, the forces we know, gravity, electromagnetism, are vibrations of tiny strings, and black holes might be gateways to other brains. But critics argue it's untestable, a mathematical marvel without experimental footing. Then there's causal set theory, where space-time isn't smooth but a shimmering network of discrete events, like pixels in a cosmic video. Each moment connects only to its immediate neighbors, crafting time's arrow from sheer sequence. It's a radical rethink. No infinity, no singularities, just pure causality knitting reality together. Stephen Wolfram takes a computational angle, suggesting the universe runs on hypergraph rules, evolving via simple programs that generate staggering complexity. His meta-rule posits that beneath all theories lies a deeper algorithm, a code that spawns everything from quantum fields to galaxy clusters. Yet the haunting question remains, even if we find this theory, could we comprehend it? Gödel's incompleteness theorem hints that some truths might forever outrun logic. Perhaps reality's ultimate nature isn't just unknown but unknowable, a humbling frontier where science, philosophy, and wonder collide. What's clear is this: each attempt, from vibrating strings to cosmic code, brings us closer to grasping the universe's deepest secret, one breathtaking idea at a time. But what does all this mean for our search for truth? As we push the boundaries of understanding, we're forced to confront the limits of knowledge itself. Kurt Gödel's incompleteness theorems shattered the dream of a perfectly logical universe by proving that any sufficiently complex system will always contain truths that cannot be proven within that system. In other words, there may always be aspects of reality that remain just beyond the reach of our mathematics and logic. David Hume took this idea even further centuries earlier, arguing that human reason has fundamental limits when it comes to grasping ultimate truths. He famously questioned whether we can ever truly know the causes behind events we observe, or if we're simply conditioned to see patterns where none may exist. This skepticism strikes at the heart of our quest for a final theory. Here's the paradox: the more we uncover about reality, the more we realize how much might lie outside our comprehension. Could the true nature of the universe be something our minds simply aren't built to grasp? Or is this very idea just another limitation we'll eventually transcend? These aren't just philosophical musings, they shape how science progresses. Every generation believes it's on the verge of solving the great mysteries, only to discover new layers of complexity. Yet this recognition of limits isn't defeat, it's liberation. It means the universe will always have more wonders to reveal, more questions to spark our curiosity. The journey of discovery never truly ends, so as we stand at the edge of understanding, peering into the unknown, perhaps the greatest wisdom lies in embracing both our knowledge and our ignorance, the known and the forever mysterious. After all, the most profound truth might be this: reality is vast enough to hold both. Now that we've ventured through these mind-bending theories, let's take a step back and marvel at how each one turns our everyday understanding of reality upside down. From the idea that we might be living in a vast computer simulation to the possibility that consciousness itself shapes the universe, every theory challenges what we thought we knew. Some suggest time is an illusion, while others argue that multiple versions of us exist in parallel worlds. There's even the wild notion that our entire cosmos could be nothing more than a hologram projected from the edges of space. What's fascinating is how many of these ideas, no matter how strange they sound, are backed by serious science, quantum physics, cosmology, and even neuroscience. They push the limits of our imagination while forcing us to question whether reality is as solid and predictable as it seems. So here's the big question for you. After hearing all these possibilities, which one resonates with you the most? Do you find yourself drawn to the elegant simplicity of the holographic principle, or does the infinite branching of the multiverse theory spark your curiosity? Maybe you're convinced that consciousness is the fundamental fabric of everything. Whatever your take, let's keep the conversation going. Drop your favorite theory in the comments below and tell us why it stands out to you. If you enjoyed this journey to the edge of understanding, don't forget to hit that subscribe button and ring the notification bell. There's always more to explore, more mysteries to unravel, and more mind-expanding content on the way. Thanks for joining me on this adventure through the nature of reality. Stay curious, and I'll see you in the next video.